ಇನ್ನು ಎರಡು ಕಾರ್ಯಕ್ರಮ ಒಂದು ಶ್ರೀಮಂತಿಕೆ ಪಕ್ಕನಾದ ತಲೆಮಾರು ಸ್ವಾಮಿ ಕೊಡ್ತಾನೆ ಶಾಟಿ ಟೀಚರ್ ಎಂಟ್ರ ಅಡೇ ಮಂತ್ರಿ ಇಲ್ಲ ಅದು ಅರ್ಥ ಆಯ್ತು ಟೀಚರ್ ಮಾರ್ಕ್ಸ್ ಟೀಚರ್ಗಳೆಲ್ಲ
Good morning, all. Seeking the blessings of Sri Lord Krishna and His Holiness Sri H. Vishwapriyatirtha Swamiji, it's my great privilege to welcome you all to the inaugural function of International Conference on Discrete Mathematics and Combinatorics, ICDMC 2020-21. Gaining knowledge is the first step to wisdom, but sharing it is the first step to humanity. As a stepping stone, we, the Department of Mathematics, Poornaprajna Postgraduate Center, Udupi, are pleased to organize the International Conference on Discrete Mathematics and Combinatorics, ICDMC 2020-21. Prayer is aligning ourselves with the purpose of God. May I request Ms. Deepika Bhatt, Faculty, Department of Mathematics, to invoke the blessings of Almighty.
ಗಜವದನಾ ಬೇಡುವೆ ಗೌರಿ ತನಯ ಗಜವದನಾ ಬೇಡುವೆ ಗೌರಿ ತನಯ ತ್ರಿಜಗವಂದಿತನೇ ಸುಜನರ ಪೊರೆವನೇ ಗಜವದನಾ ಬೇಡುವೆ ಗೌರಿ ತನಯ ತ್ರಿಜಗವಂದಿತನೇ ಸುಜನರ ಪೊರೆವನೇ ಗಜವದನಾ ಬೇಡುವೆ ಪಾಶಾಂಕುಶಧರ ಪರಮ ಪವಿತ್ರ ಪಾಶಾಂಕುಶಧರ ಪರಮ ಪವಿತ್ರ ಮೂಷಿಕ ವಾಹನ ಮುನಿಜನ ಪ್ರೇಮ ಮೂಷಿಕ ವಾಹನ ಮುನಿಜನ ಪ್ರೇಮ ಗಜವದನಾ ಬೇಡುವೆ ಗೌರಿ ತನಯ ತ್ರಿಜಗವಂದಿತನೇ ಸುಜನರ ಪೊರೆವನೇ ಗಜವದನಾ ಬೇಡುವೆ ಗಜವದನಾ ಬೇಡುವೆ ಗಜವದನಾ ಬೇಡುವೆ त्वमेव माता च पिता त्वमेव त्वमेव बन्धुश्च सखा त्वमेव त्वमेव विद्या द्रविणं त्वमेव त्वमेव सर्वं मम देवदेव ॐ पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ॐ शान्ति शान्ति शान्तिः
Thank you for the beautiful rendering, ma'am. Now, may I request Dr. Raghavendra A., Principal, Poornaprajna College, to honor and seek the blessings of His Holiness Sri Sri H. Vishwapriyatirtha Swamiji with fruitfulness.
Narayana. Narayana, Narayana, Narayana.
Thank you, sir. The Udupi Sri Advar Education Council, the apex managing body of Poornaprajna educational institutions, manages 27 institutions, spanning the whole spectrum of education from the primary level to the postgraduate level, realizing the need for higher education in the semi-urban area in 1960. Currently, our college is affiliated to Mangalore University. The postgraduate course in mathematics was introduced in 2015, promoting the importance of mathematics and to fulfill the desire of pursuing higher education to the students of rural and urban area, facilitating the students with numerous research and teaching-oriented activities. Now, may I request Dr. Prasanna Pujari, Faculty, Department of Mathematics, Poornaprajna College, and Organizing Secretary, ICDMC 2020-21, to brief about the conference.
I hope about it.
Some sound is coming now. Start. Yeah, Swami, yes. Sound.
Every work has to go to pass through hundreds of difficulties before succeeding. Those that persevere will see the light sooner or later. Good morning, everyone. Seeking the blessings of Lord Sri Krishna and Mukhya Prana, my humble pranamas to Sri Vishwapriyatirtha Swamiji. First and foremost, I would like to thank our Swamiji, Management Committee, Principal, Vice Principal, and IQAC for providing me an opportunity to conduct the International Conference on Discrete Mathematics and Combinatorics 2021. A nation's future can be shaped only through shaping the young minds of nation. Quoting these great words of Sri Vibhudesha Tirtha Swamiji, the founder president of our institutions, we dedicate this conference to Sri Vibhudesha Tirtha Swamiji. The Department of Mathematics has organized two national level UGC sponsored conferences in the year 2010 and 2015. We plan to organize this international conference in the year 2020. Due to this pandemic situation, it got postponed and today we are meeting here in the virtual mode. The conference site was launched on 5th March 2021 by Sri Vishwapriyatirtha Swamiji. It is our privilege to have with us 8 eminent speakers with us for this conference. 666 participants have registered for this conference, whereas 71 participants have submitted their abstract. All the high quality papers will be considered for revision and will be published as a special issue in this conference. And there will be no article processing charge. A special thanks to our chairman of this conference, our dear principal, Dr. Raghavendra sir, for his guidance and motivation. I'm thankful to you, sir. I would like also to thank all the staff members of our institution for their constant support. I hope all of you will enjoy this conference. Thank you one and all. Thank you.
Now, may I request His Holiness Sri H. H. Vishwapriyatirtha Swamiji, President, Poornaprajna College Managing Committee, to give away the inaugural address with his words of blessings.
Purnam adah purnam idam purnat purnam udachyate purnasya purnam adaya Purnam yeva avashishyate Poornaprajna tritiyastu bhagavatkarya sadhakaha Shri Gurubhyo Namaha. This means Purnamadaha Purnamidam. This is symbol of Poornaprajna institutions. What is the meaning of this Purnamada Purnamidam? This shloka says maths. That is Purnam. This is also Purnam. Purnam Adaha. Purnam Idam. Rishis says this mantra towards Lord to pray him. What is the meaning? Purnam adaha. Just like, for example, we light the lamp. From one lamp, we take one more light. But from which light we took, that is also Purnam. The taken light also Purnam. That is the same meaning. It is example. Rama, Krishna, Matsya, Kurma, these are the incarnations of Lord Vishnu, Lord Narayana. Lord is himself a light. Ramakrishnas themselves also lights. Ramakrishna's lights came out of that Narayana light. That is also Purnam. This is also Purnam, just like lights. Not just like your paddies, gathering of the paddies. There is a paddy is there, paddy is there. Let us take some paddies from that, but that is not. This is also not Purnam. But in light, that is also Purnam. This is also Purnam. Lord Vishnu also Purnam. Purnam means infinitive. That Ramakrishnas came from that, from Narayana. These Rupams also, these incarnations also Purnam means infinitive. So infinitive minus infinitive or infinitive plus infinitive, whatever it may be, but both are infinitive. It is the one kind of maths. That is why in our Poornaprajna college, it is the our symbol, prayer, Purnam Adaha Purnam Idam. To all subjects, not only maths, to all subjects, let it be physics or chemistry or biology, to each and every subject, that is a contribution of our olden rishis, rishi munis, especially to the maths also. Special thing is, to that maths, our rishis has given what? 0. No other countries perhaps has given our India, not India, our Bharat, who came this name from Bharata, king, from that it is called Bharata. So in olden days, our Rishi Munis, they are not only musicians, maths teachers, they physics teachers also. No, nowadays teacher means is 1 in 1. Sometimes 2 in 1, but in rishis, not 1 in 1 or 2 in 1, all in 1. All they know physics, chemistry, biology, maths, each and everything. Especially they have given to this math their 0. Then that is why then onwards it became as infinitive. So Poornaprajna is host all throughout the country, not only country, it is international. We call it Antarashtriya. Maths conference is going on. Our college's name is Poornaprajna. Poornaprajna means we call him Madhvacharya. Means third incarnation of Anjaneya. First Anjaneya, second Bhimasena, third one is Madhvacharya or Poornaprajna, third incarnation of. By his name, this college we are running this college. So my faculty members, they has contributed their full efforts to this function. I pray Lord Mukhya Prana and Shri Krishna to become the function success. All the best. Thank you. Again in English.
I bow to your blessing, Swamiji. Now, I request Dr. Raghavendra A., Principal, Poornaprajna College and Chairman, ICTMC 2020-21 to give away the presidential remarks.
Good morning, everyone. offering my pranamas and prayers to Lord Krishna and Mukhya Prana. I would like to seek blessings from His Holiness Sri Sri Vishwapriya Tirtha Swamiji, who is amongst us now. He is the President of Udupi Sri Adamarmad Education Council, which was founded by his Guru Sri Sri Ubadesha Tirtha Swamiji. We are very proud to present this seminar, international conference, to the world of mathematics. This is an opportunity for young learners to bring out their talents and get oriented in research in mathematics. Poornaprajna College is an affiliated college to Mangalore University, offering most of the undergraduate courses like Bachelor of Science, Bachelor of Commerce, Bachelor of Business Administration, Bachelor of Arts. Along with that, we have postgraduate courses, Masters in Mathematics, then Masters in Commerce. For last 60 years, a dedicated set of teachers with the blessings from Swamijis have been serving the society. This conference is a full-fledged conference to be on record, maybe the first of its kind, organized by an undergraduate college in a semi-urban area. It's not only with invited speakers, then invited lectures. There are young researchers who will be presenting their papers. Also, there are opportunities for them to publish their papers in a dedicated journal. So, in this sense, we have been organizing now a full-fledged international conference. Being small in size, we look forward for greater such success in future. The Department of Mathematics, which has to be lauded for their effort in bringing out this, including me, we are 10 members in the team who have have come out with this novel international conference. The team has been working out, has planned this conference for last 1 year, and because of the pandemic, as the organizing secretary said, we had to face a lot of problems. In spite of that, we are coming out today with 2 days conference, which is being witnessed throughout the world. And I wish all the success to the committee in bringing out this conference. I would like to extend my welcome to the invited speakers who will be presenting, who will be delivering their resourceful lectures, and I would like to all the young researchers who will be presenting their papers on behalf of Poornaprajna College and Poornaprajna College Managing Committee. We wish you all the best. Thank you.
I thank you, sir. Start where you are, use what you have, and do what you can. Hoping that you will all benefit out of this conference, we are concluding the formal inaugural program. Thank you. Have a pleasant day. Here we have an announcement. We'll have the first session by the keynote speaker, Dr. Suryanarayana B., Professor, Dr. Ambedkar Institute of Technology, Bangalore, at sharp 10 a.m. Stay tuned in. Thank you. Thank you, one and all.
ನಮಸ್ಕಾರ ಸುಧಾಕರ್.
ನಮಸ್ಕಾರ ಸೂರ್ಯ.
ಹೇಗಿದ್ದೀರಾ?
ಈ
ಕೇಳಿಸ್ತಾ ಇದೆನಾ? ಕೇಳಿಸ್ತಾ ಇದೆನಾ? ಕೇಳಿಸ್ತಾ ಇದೆನಾ?
ಕೇಳಿಸ್ತಾ ಇದೆ ಸರ್.
ಸರಿ. ಯಾಕೆಂದ್ರೆ ಕ್ಯಾಮರಾನೇ ಬರ್ತಾ ಇಲ್ಲ.
ಪ್ರಸನ್ನ, should I start?
No, copy the mail.
Good morning all. We have with us Dr. Poornaprajna B, Professor, Dr. Ambedkar Institute of Technology, Bangalore, as a keynote speaker of the today's program. Now, we also have Dr. Sudhakar Ji, Professor and Head Department of Mathematics, MIT, Manipal Academy of Higher Education, to chair the session. Sir has published around 21 research articles, mainly in graph theory. Sir has guided 4 PhD students and presently Sir is guiding 2 students. May I request Dr. Sudhakar Ji to lead the session? Over to you, sir.
Okay. Can you hear me?
Yes, sir.
Okay. I'm very pleased to introduce today's keynote speaker, Professor Dr. Poornaprajna. Dr. Poornaprajna had his BSc and MSc from Mangalore University and PhD from Bangalore University under the guidance of late Professor Harinath. He has a MTech and a honorary Doctor of Science degree to his credit. Professor Poornaprajna is presently working as Professor in the Department of Mathematics, Dr. Ambedkar Institute of Technology, Bangalore. He has got 33 years of experience in teaching as well as research. He has successfully guided 20 research scholars and has published more than 90 research articles in reputed national and international journals. Also, he has published more than 12 textbooks for undergraduate students and MTech students. He has received many awards like Vision Group of Science and Technology Best Publication Award, which he has received from Padma Vibhushana C.N.R. Rao, in the year 2018, and he is reviewer for many national and international journals like American Mathematical Review, Ars Combinatorica, etc. Apart from all this, Suryanarayana has a very peculiar quality, and that is he is ever ready to help any research scholars, teachers, or anybody who wants to learn mathematics or learn in particular graph theory. He conducts weekly classes and he invites anybody and everybody who is interested in learning graph theory combinatorics to his house, listen to them carefully, guide them, show them direction, proper direction, and maybe like it was to Paul Erdős, it is to Suryanarayana. Doing mathematics is a social responsibility. With this brief introduction, I welcome and I invite Professor Dr. Suryanarayana to deliver his keynote address. Welcome to you, sir.
Thank you, Sudhakar, for your nice introduction. I'm very much happy to be one of the speakers for this international conference, which is conducted by Poornaprajna Udupi College, Poornaprajna College Udupi, with listening to all the participants and paper presenters for good success in the conference. I now deliver a small talk as an introduction to calligraphs and its applications. One of the interesting applications, so many applications are there, mathematical applications, but one of the new application we can easily think to apply to our Karnataka music. Okay. So this is one of the different types of talas we have in our culture, in Yakshagana and some other Karnataka Sangeet also. I think some of them may be motivated to work in the direction with this small introductory talk on such more applicable and non-mathematical field where you can apply mathematics also. Am I audible?
Yes, you are.
Okay. In between, I will write and I will give the small assignments also. Okay. Now I will start my talk on calligraphs. Okay. We'll begin with the small introduction to the groups with some examples in a different way, and we'll see the meaning of generators and also the meaning of relators in the sense of groups. Later, we will try to construct or associate the graphs for each groups. Namely, there are so many graphs are associated with the groups right from the polia. We are now dealing with our calligraphs toward this, and we'll go for the new terminology, campanology, that is the study of bell ringing. What is the problem in bell ringing, and how can we solve their problem using calligraphs? This is the brief introduction. We are now spending 1 hour to understand the applications of groups, graphs to the field of non-mathematical area, bell ringing. All of you know, just to recall for the new or old persons, those who are not teaching group theory, very simple definition of group. It's an ordered pair G star, it's a groupoid, where star is the binary operation which satisfies the associative law. First one. The second one, the existence of identity. The third one is existence of inverse. With this three, along with that groupoid property the closure law holds, we'll say a group with the binary star algebra, binary structure star is a group. Now example for the group, we'll take Zn. Zn, you know what is Zn? Zn is the group of rotations of on n gones. Okay, so we have a n gone, here the 6 faces gone, 6 gone. Okay, now you keep this one up, or then this is the original position of this 6 gone. 1 coincides to the 1, 2 coincides to, that will write as here 1. Here 1 goes to 1. Can you see the pointer?
Yes.
Yes, sir.
2 goes to 2. That 3 goes to 3. 4 goes to 4. That is nothing but, I'll call that the 0 position. No rotation, 0 rotation. That coincides to the first element of this Z6 I'll call, because the 6 gone this I taken. Now you can rotate this anti-clockwise or clockwise. I'll rotate this clockwise. If I rotate now clockwise 90, so exactly 90 degree, I'm getting the new polygon. It is not the same as the original. It will, the shape will not coincide to the original one. So original was this portion. Okay, this is the shape. It is not exactly the same as this shape. So now let us rotate this only 60 degree. So then my 1 exactly coincides to 2, 2 coincides to 3. So I have written here, this is my first rotation that takes 1 to the position of 2, 2 to the position of 3, 3 to the position of 4, and so on. Again, further you rotate. Okay. Again, go on rotate. We're getting the, finally, we'll reach this position and going to 6. 1 goes to 6. Okay, written here. The finally, when you move on further 60 degree, you're going back to the starting point 0. Okay. So there are 6 possibilities. The first 60 degree, next 120 degree, next 180 degree, 60 rotations. We are getting these 6 permutations. Okay. These permutations we write symbolically. That is very important for us now. The one rotation of 60 degree, I'll denote it by A, the symbol A. A denote the right anti-clockwise direction, rotation in clockwise direction, 60 degree. So A power 0 means there is no rotation. It's in the starting point. A power 1 means 1 rotation. Second one is A square. That means A and A again, A and A. Okay. That way, right finally is A power 5. So these are the elements. I'll replace the elements 0, 1, 2, etc. 5 by A power 0, A power 1, A power 2, etc. A power 5. Now there is a sense here. A again A. That will write as A and A. A and A and is always denoted by product dot. R is denoted by plus. So if you write A and A, then we'll write here A square and A power 3. That is A dot A power 5. 3 total is A power 5. Okay, bases are same powers are added with that law. Therefore, it exactly coincides to the position 5. In that sense, so we are now writing in the multiplication and A But in the new notation, we'll write like this. Now, another group we have called dihedral group. It is permutation of n along with the rotation also. So there are 6 permutations, a power 0, a power 1, just like the previous one, 60-degree rotations. And also we have one more rotation here, okay, that is 180-degree rotation. That means flip-flop rotation, okay, that I'll explain here. Just you write the polygon, okay, just you reverse this and write like this, keep like this. Again you are getting the same polygon, keep the polygon. This is original position 1, 2, 3, 4, 5, 6. You rotate this 180-degree, 1 and 6, 2 becomes here, so it comes to this position, 3, 4, 5, 6, okay. Original positions are changing, so that is the 180-degree rotation denoted by B. B denotes the 180-degree rotation. So A into B denotes first A rotation, then B rotation. So totally, we are having total A rotations 5, 6 total A40 including identity. For each rotation, I can flip also. So I'm getting total 10 elements. Okay. So in general, suppose if you have n gone, then we'll get 2n possibilities, elements here that are all denoted here. A40 is nothing but identity. A41 is nothing but 1, 2, 3. In cyclic notation, we write this as 1 goes to 2, 2 goes to 3. We write like this. Okay. Here 1 goes to 1, 2 goes to 6. So 2 goes to 6. Again 6 goes to 2. So 1 goes to 1. I am not written here. You are not writing. 2 goes to 6. 6 goes to 2. We are writing here. And then 2, at least length 2 should be. 3 goes to 5. 5 goes to 3. That we are writing here. Okay. This is the notation. Instead of A0, you can write like this also. This is the this shows that D2n is a subgroup of Sn. Okay. So in general, I written here only 6 elements. N1. So my rotations are sorry, my n is now 3 for this. Sorry, there is a disturbance. N is 3 now. Sorry, 6 here. So the 12 elements you are getting is generated by A and B. Here writing A, comma B indicates these are the generators. Where sorry, here n is 3. Okay, n is 3 here. Sorry, for this n is, wait a minute, I disturbed it. N is okay. N is 6. So A power 6 equal to B square equal to E. A power 5 times B equal to BA. So you can use this relation. This is called relation. Suppose without this relation, if you write any AB, all strings will get that such groups are called free groups. So we have a relation here that A and B should satisfy this relation. Then you write the table for this. Okay. Now let us go to another group Sn. This is the set of all permutations of n objects. Okay, that is nothing but the set of all bijections from 1 to n to 1 to n itself. So n is nothing but the first set integers. Now we write S3. S3 contains exactly 3 factorial elements, the 6 elements. Here, first one, this we can also think as a dihedral group on 3 elements. The 6 we are getting. Here, first rotation, that is 180 rotation, that is nothing but my A. Again, so 120 rotation, that means this 1 goes to the place of 2, that is 120 rotation of the plane. Here again, this is, we are interchanging 2 and 3, that is nothing but a rotation B. So S3, you can write S3, you can also write as a D6. It is the first non-abelian group on 6 elements, smallest one. So the relator is A cube equal to B square equal to E. That means the order of A is 3, order of B is 2, and A and B are related by A square B equal to BA. If AB equal to BA, it is understood that the group is abelian. If you write G is an abelian group, then this is not necessary, right? Without this understood that it's always abelian. Now we have tried one more relation. This relation shows that it's not abelian. Now, for n greater than or equal to 2, the symmetric group Sn is generated by its transpositions. Okay, what do you mean by generating set? Out of these elements, there are 6 elements that are A power 0, A power 1, that is A power 0 is 1 identity, A square B, A, B, B, A. You can choose some of the elements. I took here the first element as A, the second element as B. Okay. I told A and B are generators. What do you mean by this? Is all other elements of this group can be written using only these 2 elements. Product of this A into A or A into B or A into B into B. These are all, you can go obtain, all other elements can be obtained using this. This group may have some other generators also. Okay. Some of them maybe just a subset. They are not generators. If the elements of the subset, all the elements of the group can be obtained by using the elements on the set only, then we can say that is the generator set. That means if you say S is a generating set, then general set of a group G, then G has no proper subset containing S. That's the meaning. Proper subgroup containing S. Now, if S, the symmetric group Sn is generated by its transpositions, that is length 2. Okay, first one, that very elementary theorem. Any set of transpositions which generates a symmetric group Sn has to contain at least n-1 transpositions. This is very, very, very important result. And Kelly told that every group isomorphic to a subgroup of some symmetric group. That means if G is a group of order n, then G is isomorphic to subgroup of Sn. Okay. The example previously we saw Sn and Zn. Okay. Zn is the group of order n. That is actually a subgroup of Sn. Now, in the S6, so this is S3, D6 already. So for this graph, for this rotations, with using this is S3, sorry, using this relator and generators A and B, how to write a table. So just for the first table is for Z5. Z5 contains 5 elements 0, 1, 2, etc. 4, 5 up to 4 Z5. So you write a power 0 is 1, 1 is 1. A power 0 into a power 1. You're adding the powers of this and writing a power 1. This is very simple one. But here, this is the group which is abelian. There is no problem, we can write immediately. But here, the second table, we have to use the relator now here to write the group. This is D8 group D8, writing here now. D8 generated by 2 elements. How to write now? For some of the entries I have filled here. I kept here the question mark to fill the entry just by knowing the relator. So question mark is nothing but AQ star ABA. Okay, that means this A cube and BA you are multiplying now. A cube into BA is A cube into, we have the relation here, BA is cube B. We write now A cube B. Don't use the abelian property, commutative law fails here. A power 6 into B. That means A power 4 is nothing but identity element here. So this is identity element into A square into B. So we'll get just A square into B. So this element should be A square into B. See, it is not repeated in our row. So what is Cayley table? None of the rows, the elements in the row as well as in the column repeats. This is the way you can write. Abelian also can obtain diagonal symmetry in diagonal symmetry. Principal diagonal symmetry of the table shows the group is abelian. These are all simple properties we studied. Now using this now, I'm going to write Cayley graph. Okay, I've completely prepared the table here for D8 group. I'm going to write a Cayley graph now, D8, on the for the set S containing A and B. How to write the Cayley graph? The given group G, okay, my group G is D8, and the subset S. I took S as A comma B. This contains no identity element, okay, of G. The Cayley graph, Cayley G comma S, is an undirected graph. We should not write the directions. We neglect the direction. Whose vertex at G contains the edge. Okay, vertex set graph on whose vertex set is nothing but the elements of G and contains the edge from G to SG. D to SG, the form G to SG. For example, I write now first element is 1. All the elements of this 1, A square, A, B cube, all you would write here, that are the vertices of the graph. Now, for the vertex 1, I'll take the element A is here, okay. The elements from edge from G to SG. What do you mean by that? Let us understand that. If you have a vertex X here, if this edge corresponds to the element A in the set S, A belongs to S, then this goes to Y only if Y is in the form AX, A into X. That means X to AX in that form. When Y is AX, Y should be in the table. Y should be in the table under X corresponds to A. So A into X equal to Y. So in your table, check in your table for the 8th row, okay, Xth column, what the element is there? That element is adjacent to this X under A. Now let us see for this here A, for 1 to A, let us see the table. See the table correspond to 8th row. 8th row, let us see where one appear in the column. That the first column we have 1. The element here is A. This element is A. Therefore, 1 goes to A. Okay, and second edge corresponds to the B in next element. Next element here in S is B. For the second element, let us go to the row B, and column 1, the element B is there. So I wrote here B. Okay. So this is the way I write the edges from 1. Okay. Now let us repeat the same process from A onwards. Okay. From A, I have write 2 edges, one for corresponding to A, one corresponding to B. Okay. Now A to A, you have to read the row correspond to this A, edge A, and column correspond to A. The edge A to column A, that goes to A square. Okay. That means this edge goes to A square. And B, for this B, Bth row, 8th column, Bth row, 8th column, the element is Ba. So this second edge goes to Ba. Okay. First one is A square, second one is Ba. Okay. Now this A work is over. I made yellow this vertex to indicate all the edges from this vertex is complete now. Now let us see this B. Let us start from the work from B. I have write 2 edges from B, one for A, one for B. So B, 8th row, Bth column. 8th row, Bth column, I have an edge, I have element AB here. So therefore B, I write to AB. This is an edge from B to AB, correspond to the HA. So this edge we call the edge generated by the element A. Similarly for B, Bth column, Bth row, Bth column, Bth row, Bth column, we have one identity, one already we written, don't include extra vertex. Okay. B1 already we wrote edge here. Without direction we are writing. So one direction 1 to B, second one is B to 1. This second one indicates B to 1. We are neglecting the direction. Therefore, direction is not necessary. Don't repeat multiple edges. Okay, we remove this. Then B work is over. Now let us go to next A square. A square again 2 edges A and B. A row, A square element. We have A cube. So you write, or I wrote A cube here. Bth row, A square column, Bth row, A square column, that is A square B is there. So I wrote here A square. A cube and A square B are new elements, therefore I have not written the returning edge here. Okay. Similarly, so next to BA, I have started with BA, A and B. B is actually B. One can think why I have not written B because B into B is identity element. The order of B is 2. Whenever order of B is 2, returning edge is the same. So we are getting A to X to Y and Y to X also. Whenever B is equal to B inverse. This is the possibility. Therefore, all green edges I am writing only once. 2 yellow red edges we are getting. One is incoming, one is outgoing. That is one for corresponding to inverse element of A, one corresponding to direct element of A. So when you complete this, okay, this completes. When you complete all, we are getting this. Okay, this is the Kelly graph corresponding to the dihedral group D8. Next, what are the properties known for the Kelly graphs? There are a lot of work done on Kelly graphs. Still, there are so many problems are open. One is Arthur Kelly, who identified a red color cycles here, see, that he called pigons. Okay, here identified there is a cycle of length here 1, 2, 3, 4. Okay, that correspond to A. That means the cycle length indicates the order of the element. Here B to B, again there is a cycle of length 2 here, because B to B and B inverse, we have not written multiple edges, therefore order of B is 2. I can identify order of the elements in this. Okay, and if you write yes, all the elements of except the identity element you are leaving to just to avoid loops here. If you include loops, then there is no problem, you can write A itself. So then all possible edges we are getting. I wrote only edges A and B here. Okay, and its inverse. by taking S equal to only two elements A and B. Now if I take S equal to all the elements except identity, then we are getting a complete graph whose edges are colored with the corresponding elements. Okay. Kerning graph is connected. So now this is connected. If and only if S generates A. I took S equal to A and B. Using A and B, I can write all the elements of the group. All the elements I can write, because how to write A square B? 1 into A. Okay, 1 into A into B, A into B into A. That means A square will get. Using A and B, I can write all these elements. Okay, because of this just generating set I took. If there is not, suppose you take just A and AB only, two other elements. There are 8 elements total. I took 2 elements. You can take other elements, 2 or 3. Suppose this graph is disconnected, then that's not a generating set. Further, for every finite group A, it is given as a conjecture in 1998. For every finite group, there is generating set S such that K A, S is Hamiltonian. Okay. What we did here, we calculated a Hamiltonian cycle in the Kelly A, A, that is Kelly graph, complete Kelly graph. In complete Kelly graph, complete graph always contains Hamiltonian cycle. You find a Hamiltonian cycle contains minimum number of colors. Okay, each color you find for each color you write a set containing all the colors. Okay, that color set S itself a generating set for the graph, and the graph is for that set S. The graph is always Kelly graph is always Hamiltonian. So this theorem is now settled. There are directed Kelly graphs that are not Hamiltonian. Okay, there are some graphs which are not Hamiltonian. Undirected graph also, some cases it is proved this Hamiltonian whenever the order of A and order of P are generated by 2 elements and the orders are relative prime. Now this is this Kelly graph. If you write the Kelly graph for A is a group that is nothing but S4. A is a group S4 with respect to this generating sets. Okay, these are the permutations 1, 2, 3, 4, 5, 6. This is up to n minus 1 transpositions here. Here also n minus 1. So these 3 elements generates the group S4. Therefore, it is Hamiltonian. These are some preliminaries. Now let us go to the interesting topic of today, that is Combinatorics. Okay. We know that in Kannada we say Kampana means it is a vibration. Okay. Combinatorics is the study of bell ringing. Okay. In bell ringing, we will keep the bells. N bells will keep. Bell 1, first bell represent treble. The last bell N we call the tenor. The operation of ringing from row to row is calculated through permutations and will be denoted as a change. Okay. See, now this is 1, 2, 3. That means the first person holding the bell, this is bell 1. Second person holding the second bell 2. The third person holding the bell 3 rings third time. So this first preference, first he will ring, next second, next third. Okay. See, this is the order of ringing. So this is one switch here. Okay. No, sorry, this is one first 1 to represent. This is the ringing of first ringing of all the n bells. This is the order of ringing the all n bells. So the function that is nothing but the function 1, 2, 3, 4, etc. n2, 1, 2, 3, etc. n. So this is 1, 2, 3. These are the bells. This 1, 2, 3, etc. n are bells. This below what I written here, the order of ringing the bells. The person who is first person should ring first. Second person should ring. Next one, third person should. So change ringing is represented through the permutations Sn. Okay. Now this is the first one. Now we will change now. How to order will change now. That is nothing but our permutation Sn. For example, I wrote here 1, 2, 3. This is first one. We'll get one sound. Okay. Next will sound change. Okay. Next will 2, 1, 3 item. I written here. So these are all switches. The first all the three will ring like this. Next we will switch to second one. Next we will switch to next one. Okay. Let us see here what happens now. The first one, second, third. That is for the first. Next to first to third, second. Next to second, first, third. Next one, first, second, third. Okay. So this type of sequence we are writing. This first one, second one, third, fourth. We are switching one permutation, second permutation. Okay. This some type of these permutations are very interesting. Some of them are not allowed in ringing because we have to generate all possible sounds, all possible permutations you are ring. So an extent is when a full ringing has occurred. That means out of 1 to 3, there are 1 to 3. There are 6 possibilities. 3 possible permutations are there. I wrote here 4. So all the 6 completes and return back to 1 to 3. There is a starting identity. Return back to identity 3. Then we say an extent is occurred. Is when the full ringing has occurred. So when all the possible cycles of Sn has been rung once with the additional row of the identity, that means there are total n factorial plus 1 rows. Okay, the first one and last one repeats. Total there are n factorial permutations. All the permutations should be there except the last one. The total n factorial plus 1. There's possibility. Next, throughout these changes, the condition must follow to be a change ringing. Okay, one ringing 1, 2, 3. To quote next ringing 1, 3, 2. What the condition should follow? These are the 3 very important conditions. So the first and last change are both the identity, which is called rounds. The first one should be identity 1, 2, 3. The last one should be identity. These are called rounds. Okay, one round completes. No other change is repeated. Okay, the first one 1, 2, 3, that only repeats here. 1, 3, 2, that is not repeated anywhere. Okay, all the intermediate changes should not repeat. Second condition. The third condition is from one change to next, no bell moves placed more than one position away from its previous spot. Okay, what do you mean by that? To understand that, let us see the persons. Let us see the persons who is ringing the bell. This is first one. This is the first one, 2. This is the third person. Okay. Now there are bells here. Bell 1, bell 2, bell 3. Okay. 3 bells. I wrote here 1, 2, 3. That means first person should. First, this bell should be going by first person. This is for second, third one. This is this way. The second I wrote now 1, 3, 2. That means the first bell, first person should come in first position only. That means he is not changing his position. This bell, second bell for third person. Okay, third person should come here. That means he is moving the position, this position. Okay, second person moves to this position, and second person will ring third. The third ring 2. Okay, first one first. So movement of these persons. This person moved only one position. This person also moved put one position. So 1, 3, 2. This is not permitted here because if you want to ring the bell, the first person should. Sorry, this is 3. 3, 2, 1. 3 to 1 is not possible because to ring this bell, the first person should go to the place of third place. He has to go to the third place, and first person should come first. Okay. So the change here 3 to 2 is 1. Okay. 2 to 1 is 1. Okay. But here change is it is more than 1. This is not possible. The change between two consecutive. So a change between any two. Sorry, not this. 3, 2, 1 possible. Okay, this is possible. So 1, 3, 2 is not possible. Okay, 1, 3, 2 is not possible. 1, 3, 2. So 1 to 3, the first person should go to the third place. So 2 positions. So this is not possible. 3 to 1 is possible. So now let us see 1, 3 is there. So this is avoided in this condition. Okay. So this is not permitted. The third one is not allowed. Under these 3 conditions, you have to write a sequence now. These 3 conditions must occur in order to have a change ringing. Okay. Now let us see here whether this is a correct change ringing. So I started with 1 to 3, ending with 1 to 3. So all the possible permutations are not here. Okay. Therefore, this is not the extend ring. So now here 1, 3 is there. 1, 3 appears here. There, and also 1, 3, 2 repeats. 1, 3 repeats. This is not permitted. Okay. This you can ring the bell, but this is not permitted because it takes more time. Okay. Each change should take maximum 2 seconds. It is calculated there. Now, this is also not satisfying because 1, 3, the change here is 2. Okay. Let us now go to, okay, what are the principles in bell ringing? There are 2 principles, one principles and methods. Methods are different and principles are different. So you have to understand what is methods, what is principles in this. There are 3 addition. There are some other conditions also. Mathematicians we are concentrating only these 2 conditions. We can impose other conditions also. So what is method? Method are when all bells have same work except one bell. One bell is not working, so that you are not ringing that bell. All others are equally likely. The principles are not like that. All bells are equally likely. No bell is fixed. Okay. Here first one bell is fixed. For example, let us see this. In this ringing, first we are taking 1, 2, 3, 4. Next we'll go to 2, 1, 3, 4. This throughout this 4 is fixed here. Okay. Once this cycle is complete, we'll go to next one. Next one, second bell is fixed. Next one, first bell is fixed. Last one, third bell is fixed. So this is complete extent. All 24 plus 1, 25 changes. So for each time, one bell is fixed. So this is a method of changing. So other one is, this is a principle. Okay. Here, none of them are fixed. So one is changing here. The 4 is one will go here. The 2 also changes. The second, the third, fourth also changing. The third, 3 also changing. None of them are fixed here. So this is fixed for instant. Second here is fixed instant. So this second one is the principle. First one is the method. How to determine methods and principles in using calligraph. Okay, we allow some more positions. We are allowed so many position changes. Each change is called switch. So 1, 2, 3, 1, 3, 2. So we are going to switch. So that are called switches. Depends on n. Switches be represented by cycles. Okay, each one just like edge. You are writing a generators. Okay. A is the generator for the edge. We will write such X to Y through A is the edge. A is the switch now. The switch is X to Y. First we consider the three bell cases. Let us understand first. We may exchange first position with the second position. The second with the third, but not with first one with the third. Okay. Third condition 3 will not allow. With that situation, since 3 bells will have switches like this. 1, 2. Third person cannot move. 1, 2 on 2 to 3. So only these are the 2 possible switches. For 4 bell, we have 1, 2, 1, 2, 3, 3, 4, 4. That means only one moment or one position. So 2, 3, first person and fourth person are not moving. 2 and 3 interchanging with one position. So here 3 and 4. Here 2 persons are, sorry, 2 moments happens. One goes to the position of 2, 2 goes to the position of 1, 3 and 4 interchanging. So simultaneously there are 2 switches here. Okay. This is permitted switch because switching between only adjacent places. So 4 bells have total 4 switches, 3 bell, 2 switches. So you can find out how many switches are there using Fibonacci sequence. Fibonacci sequence 1, 1, 2, 3, 5, 8 like that. So this is F1. F2, F3, F4. So Fn is calculated using the formula Fn minus 1 plus Fn minus 2. This is the Fibonacci sequence. So if I take n equal to, sorry, n equal to fourth one, sorry, n equal to F4, okay, 8, 4 bells, okay, this is 4, F1, F2, F3, F4, F5, okay. There are 5 possibilities, 5 minus 1, the Fibonacci number, fourth Fibonacci number is 5, 5 minus 1 is 4, there are 4 switches here, okay. First one is F0, okay, right. So this is for 4 switches, 5 switches, for 5 switches, what are the possibilities? We have 1, 2, 3, 4, 5. 5 switches. One possibility is 1, 2. Other possibilities 1, 3 is not possible. 2, 3 is possible. Okay, next adjacent 3, 4 is possible. Next 1, 2, 3, 4 is possible. Any other? Adjacent place only changes. 1, 2 changes. 2, 3, 3, 4. You see now there are total here 8, 13. Sorry, 7 total. 7. There should be 7 total. So 1, 2, 3. 1, 2, 3 is possible. 1 goes to the position. Okay, this is 1, 2, 3 is possible. It's not possible. Okay. There are 7 possibilities. So it is given by the Fibonacci number Fn minus 1. So now, if there are 3 bells are there, we add this suffix singles. 4 bells are there, minimus for all discussion. 5 bells are there. We'll write discuss. Okay. For assuming for single bell 2 seconds, 1 change, 2 seconds are necessary. So there are 4 changes here possible. There are 7 changes possible with 3. Therefore, we require 14 seconds to extend to ring all the possibilities. For 5, we require 4 minutes. Suppose if somebody given 10 bells, we can continue this ringing without repetition for 84 days. Okay, for each change by taking 2 seconds. Okay, suppose 16 bells are given. Continuously, you can ring the bell without repetitions for this much years. This is calculated. Now, how to write the switchings using our calligraph. To understand that, S3 is very simple, so I prepare the table of S4 here. Okay, table of S4 I prepared here for the purpose of explanation. Okay, here I denoted I as identity, A as the permutation 1, 2, 3, 4. That means 1 goes to 1, 2 goes to 2, 3 goes to 4, 4 goes to 3. Okay, that means 1, 2, 1, 2, 4, 3. So second one is 1, 3, 4, 2, 3 I written as B. That means 1 goes to 3, 3 goes to 1, 1 goes to 1, 2, 3 goes to 2. Okay, 4 goes to 4. That one. 4 goes to 4. That 4 only changes 1, 3, 2. We can write this as 1, 3, 2. So I prepared the table here. Okay, this is the table. Using this table, as I explained earlier, by seeing this 1, 4, this changes 4 and 2. I can write this is this correspond. Okay, 1 goes to 1. 1 is fixed here. 2 goes to 4. 4 goes to 3. 3 goes to 2. So 2, 3, 4. I can write this one like this. Okay. Out of this 3, 4, you see 3, 4, only one position change. So here 1, 2, 3, 4. This is not possible. 1, 3, 4 is one position change. So this is nothing but a switch. Here 2, 3 is the switch. Here 1, 2 is the switch. None of the others are switches. 2, 4 is not a switch. The difference is 2. 2, 4, 3. 3, 4 is okay. 2, 4 is not possible. Okay, because change is 2. This is not a switch. Okay. So out of this 4, this is the only switch is simultaneous switch. So using this switch as generators, I'll take this B. This is the switch B. Sorry, this table is shifted. First one is identity. This one 3 4 is A. 3 4 correspond to A. B for 2 3. So 2 3 are represented by red color. 3 4 are represented by blue color. And next one 1 2 are represented by green color. And using this table, just like I explained previously, we write a calligraph. To write a calligraph, only these 3 rows are sufficient for corresponding edges A, B, and F. So I removed all the other rows except these 3 rows, which are important for us to write a calligraph. Using that calligraph, writing all the vertices of the graph, that vertices in S4 as the vertices of the graph, elements of S4 as the vertices of the graph. Then we'll write the edges. Okay, red edges we'll write first. Red edges corresponds to B. Okay, Bth position. 1 B. 1 goes to B. So in B, second one, A row, B column. Sorry. B red color is B. Bth row, 8th column. Bth row, 8th column is C. So A goes to C. Similarly here you let us say KJ. So Bth row, kth column. Bth row, kth column have Q. So I wrote here Q. So these are all red edges. Next we'll go to the row corresponds to A. That is blue edges. So 8th row. By seeing the 8th row only, you can write first all right green edges. Okay, these are the green edges we are getting. Next write the last green edges by seeing the last row corresponding to Fth row. This is the calligraph. So this I can write. I'll show the embedded. This is planar embedding of this. We'll get like this. Okay, planar embedding of this. So let us pass this calligraph here. Okay, we'll come back to the calligraph. This calligraph later. We'll find out one more graph. So this I can include one more switch. This switch is nothing but I can include one more switch. That's nothing but simultaneous switch also. I missed there. Only 2 3 switches I considered which are not simultaneous. We can use simultaneous switches also. Okay, it is known now using this switches. It is known that using this I can find out. Okay, using the switches in delta, I can find out a sequence of all containing all n permutations, obeying all the conditions 1 to 3.
It is there in
Okay, obtaining all 1 to 3 all the conditions if and only if this graph with the simultaneous switches also the graph is Hamiltonian. Hamiltonianity is very important. This calligraph should be Hamiltonian. Then only I can find out the switch containing all n permutations. This is the theorem by A.T. White. Okay. Now you can show that there is Hamiltonian cycle in this.
This is not.
You see slowly Hamiltonian cycle observe here, and you see I used only the it just corresponds to non-simultaneous switches. Okay, simultaneous just simply added for this. That is not necessary for this to get the Hamiltonian cycle. So I can find a complete extent of all switches containing all n permutations without using see this is the possibility. So I'm getting all the Hamiltonian cycles to come back to the starting point. So Hamiltonian cycle means starting from one vertex covering all the vertices, you will come back to the starting vertex without repeating. Okay, now we have Shreyas coset graph. Okay, this is the new graph. This is also derived by just like a calligraph. Okay, this is one of the calligraph again. Shreyas coset graph. This is for S4. S4 is the group. So Z4 is subgroup. So Z4 any S should be a subgroup of G. Then using the generator of S4, you can write like this. First you write all right cosets of S. Sorry, H G/H. We write G/H. We have. H is a subgroup. S is the generator of G. Okay. First write all right cosets you write. Okay. Correspond to H. Then you each element of delta. You multiply each right coset. So for example, For the right coset 1 to Z, one Z4, for the right coset Z4, so multiply each element of all switches. Switches are 1, 2, 3, 4, 1, 2, 3, 4, 2, 3. So this correspond, I wrote here 1, 2, 3, 4 correspond to green edge. Okay, 1, 2 corresponds to blue edge, 1, 2 correspond to green edge, 3, 4 correspond to red, black edge. So this is the identity element. There are 4 edges we are getting here. Similarly, all other edges you can write. This is correspond to second element. This from one element we multiply this one 1, 2, 3, 1 to Z4. 1 to Z4 is here. For this, all 4 edges you write. Where it goes, you write that, identify the corresponding vertices. Then that way you are write the edge. Edge is from X1, one raised coset, other raised coset. If there is an element here in delta, which takes one coset to other coset by left multiplication. This is the way you write. From afterwards, in this, let us find out all possible Hamiltonian paths, cycles in this. Okay. For example, let us. These are all the Hamiltonian cycles. These are all not decomposition. These are all possible Hamiltonian cycles. I am getting this. Okay. Previously, I wrote here double-sided. Now I remove double-sided arrow. I understood that is undirected. Okay, undirected. Now using this graph, write all possible Hamiltonian cycles. The first Hamiltonian cycle here, that means this blue and red, next blue, green, next red, again green and red, again you'll come back to the starting point. This is the Hamiltonian cycle. This, you read this Hamiltonian cycle, okay, you ask for this rule. A corresponds to 3, 4, that is the black, 2, 3, 2, 3 I wrote as B, red edge, 1, 2 I written as a green edge, 1, 2, 3, 4 written as a blue edge. So now green edge you would read as F, okay. Red edge you would read as B, okay. So now, sorry, here something, this error, there is an error in this word term. So this I'll correct it here. This is BF, not BD. So B, red, BF, BF, BF is the Hamiltonian cycle. The Hamiltonian cycle, the edges you write in order as per the Hamiltonian cycle. B, you can start from anywhere. BF, BF, BF. Okay. The second one is BF. This is nothing but our G. Again, F, B, reverse. So that written. So that I written here. BF, BF, BF. I written BF3, BFQ. Okay. Now for this transition, I will let us for each possible Hamiltonian cycles. There are 8 Hamiltonian cycles. For each Hamiltonian cycle, we do this one. Let us consider first one. First one for this, let us write BFQ computation. Starting from identity. Identity in the B is nothing but B. That is the correspond to 1, 2, 3, 4. B into F. That will be BF, BF, BF. There are 3 times. BF, B into F. By table, you see B into F corresponds to our L. That L is nothing but here. L is nothing but 3, 1, 2, 4. It will go to here. And L into B. That will go. N this way computation. Finally, we'll reach 1, 2, 3, 4. 1, 2, 3 super is nothing but identity. Okay. Identity 1, 2, 3, 4. The order is 1. Okay. Similarly, you go to the second cycle. First cycle we got order is 1. For the second cycle, I computed here. Finally, when we end up this FB, FP, FG, we'll get the 3, 1, 4, 2. That means 1 goes to 3, 2 goes to 1, 3 goes to 4, 4 goes to 2. That will write 1 goes to 3, next 3 goes to 4. We'll write this cycle. The length of this cycle is 4. There is nothing but the order of this. Okay. So now we'll find out order of each element, each cycle here. So out of the all, the first one is order 1, second one is order 2, third one is order 2, 4, next one. You find out, you take only those cycles of order 4. Don't go to any other. Okay, now first one is leave it here. The next 4, for each one, I can generate now a method. Okay, so first one you see the order 4. You observe here. 1, 1, 1 up to third one. Next again it's back, reverse back. So this is the pattern here. This pattern is called Erlin principle. Okay, I can find out the principle for corresponding to all Hamiltonian cycles of order 4. This corresponds to Erlin principle. The last one, you write the sequence like this and see that corresponds to reverse Erlin principle. Reverse Erlin principle. The first one is Erlin principle because here 4, 4, 4, 4 constant, so 2, 2, 2 constant, and this 1 goes to, and again just reverse here, you're coming down and reverse. Okay, this is the pattern. This pattern is identified by Erin. This is his principle. So there are two principles identified for the first Hamilton cycle and last Hamilton cycle. Similarly, remaining two, the pattern is this pattern. So 1, 1, 1 will continue. It will down for till the end. 2, 2, 2 will continue, and it will down for 3 end. So this is nothing but stand down principle. Okay, that corresponds to the second Hamilton cycle. The next Hamilton cycle corresponds to the reverse stand down principle. That means it is reverse. Just you flip this right, this one right top to left bottom. Okay, just reverse. Now this principle, how to write this principle? For each principle, I can find out now. So this is the planar embedding of this graph I parked somewhere. This is the Kelly graph parked somewhere. So I write a planar embedding. This is the planar embedding of the graph in the truncated octahedron. Octahedron, each corner is cut. Okay, because this goes to here, then becomes every size of the size. See 8 faces for each region you are getting. So we cut here. This is a cross cut. This is nothing but truncated octahedron. Now here in this we have to follow some rules. What is the rule here is GB cube GA. This is the this is GB cube we got first one. GB cube GA. This rule is nothing but a plain Bob rule. So that follows like this: 1, 1, 1 go and again return, again go and return. Complete 24 permutations getting in this fashion. Okay. To get that, to how to generate all these sequences, writing this by saying the table is very tedious. For that, we'll write a Hamiltonian cycle in this. Okay, what to do here is just to follow this sequence. In this cycle, first start from the identity element. This corresponds identity element. Then go to G, again B, and next from here go to B. B represent here dark circle, black edge. Next to GB, again GB. GB's cube is there. GB, again GB. Okay, again I go to G. G is red, B is black. Okay, GB cube is there, completed. GB cube is completed. Next go to G, red. Next go to A. A corresponds to here the green. Okay, this way. So in this way complete all, find out on Hamiltonian cycle. Okay. Once you find out this Hamiltonian cycle, then it is easy to write the sequence. Switches you can write now after completing. You can write the switches here, the corresponding to the vertices here. By seeing the vertices, you can write all the switches. We'll come back to the 1, 2, 3. The 1, 2, 3 is the identity starting one. So this way, for the Hamiltonian cycle, for each principle, okay, this is the first principle, GB cube in the GA. For that principle, this for each principle is first principle is here. I shown that previously. Sorry. This principle, first one. This principle, there are 25. There are 25 entries here. The first one 1, 2, 3 ends at 1, 2, 3. So you start from 1, 2, 3, 4, 2, 1, 3, 4, generate 1, 2, 3, 4. Generally go to 3, 1, 4, 2. This way. This way go. You'll get a Hamiltonian cycle. This Hamiltonian cycle. This is the Hamiltonian cycle. Sorry. This is the Hamiltonian cycle. Correspond to Erin principle and reverse Erin principle. This you can obtain by seeing the coset graph. Okay, in that coset graph. Next, these 4 principles you can find out using coset graph, and 11 methods, plain Bob methods. This is the formula for the plain Bob methods in for the S4. Okay, 11 methods are there. Each 11 methods then you can obtain by permutation of these edges 2, 4, 3. Then we'll get 11 Hamiltonian cycles. You can immediately write using this rule. You can write the Hamiltonian cycle. So using the Hamiltonian cycle, generate the sequence immediately. So 11 possibilities. Okay. I hope this is sufficient for today. There are so many investigations to be required. For example, we have extended our dihedral groups for hemigraphs. Okay, hemigraphs. We already obtained some results on hemigraphs. So just like this is for S3, and there are so many hemigraphs corresponding to dihedral graphs also obtained. For each Hamiltonian cycles, we have to identify such a ringing or something which are very applicable one. Okay. Otherwise, you have to find out some new pattern for this corresponding to some 4 principles are already defined by others. Okay. Yeah, 4 principles are defined. One is 2 principles. One is the reverse. 2 are the reverse of that. We can define some other principle also using some group methods, groups and graphs. Thank you for the organizers for giving me the opportunity to share my views, and most welcome to the participants. If you have any questions, anytime. Okay, I thank the organizers for giving me the opportunity. I thank the Sudhakar also for sharing the action. Thank you.
Okay, it is a time for questions now. If you have any question, you can ask.
Okay, you can post it in the chat box.
Yeah.
Because sometimes network issue. Sorry, in between some disturbance. Thank you.
Dear participants, if you have any queries, you can raise your hand. Sir is here to clear it out.
Hello, sir. Am I audible?
Yeah, audible.
So, for what kind of groups we can able to draw the Cayley graph, sir?
Cayley graphs for all groups, you can find out Cayley graphs. For ringing, the other groups and only S4 are used. Okay, Cayley graphs you can find out for all groups, any group.
Okay.
But non-abelian groups and non-abelian groups very difficult to construct. Okay, and directed Cayley graphs also very interesting. And there are other applications for Cayley graphs. Okay, Cayley graphs are used for interconnection networks, so for routing and construct and designing of the network architecture for how memories are interlinked and how the processors are memories and computers in systems are designed. Okay, for any. You can go through the network theory. There Cayley graphs are used through groups. Okay, some of them are defined some Cayley graphs corresponding to some other sets, which is not a Cayley graph of a group. That's also very interesting. Okay, Cayley graphs have the beautiful property is that it is regular and vertex transitive and less diameter and less degree. Okay, these are all very and less bandwidth and less bisection width. These are very, very essential for network. Okay, this is the one new area they are using Cayley graph. Therefore, I am interested in this case. Any more?
So we know the Cayley theorem that every group is isomorphic to the subgroup of a Sn. So is there necessity that n is always finite or infinite?
N is for infinite cases, no? Infinite cases.
Yeah, so if we take a Z plus, we are not able to find the subgroup of Sn which is isomorphic to Z plus, right now, sir? So so for n must be a finite or infinite that we should.
I took only finite cases. Infinite cases, so I don't know. Suppose n is finite, then there is a subgroup of order n. Okay, Sn. There is a subgroup. That is every group of order n is a subgroup of Sn. Isomer subgroup of Sn. If n is infinite, what is that n and Sn? What Sn you take? Tell me. What's good? Graph theoretically you cannot show. finite cases, okay. What SN you take?
Yes.
Any more?
Thank you.
Okay. Any other question? Any more questions? If there is no more question, we will thank Professor Surya Narayana for a wonderful talk, and those who are interested to work can contact him at any time, and he will be very useful. Thank you, Surya Narayana.
Thank you. Thank you.
I would take this opportunity to thank Dr. Suryanarayana B. Thank you, sir, for accepting our invitation and delivering such an informative session. Also, I would like to thank Dr. Sudhakar G, for chairing the session. Thank you, sir.
Thank you, sirs.
Thank you. Thank you.
Here I have an announcement. We'll be having feedback link for each session. And for this session, we'll have the feedback link in conference site. Please go through it. We'll begin the next session by 11:15. Please stay tuned in. Thank you.
Hello. Hello.
Yes.
Hello. Sir, where is the conference site where we get the feedback link? Hello. Hello.
Hello, sir. It is already in your mail, sir. We have already mailed you.
Actually, you mailed you. Okay, okay, no problem.
Good morning, all. I welcome back you again. We have with us Dr. Sudhakar Ji, Professor and Head of Department of Mathematics, MIT Manipal, Manipal Academy of Higher Education as a resource person. Sir will be speaking on the topic Neighborhood Representative Graphs. Also, we have Dr. Raghavendra A, Principal, Poornaprajna College, Udupi, and Chairman, ICDMC 2020-21 to chair the session. Sir has published 6 research articles in reputed journals, mainly in graph theory. May I request Dr. Raghavendra A, Principal, to lead the session over to you.
Good morning, everyone. Good morning, everyone. I hope I am audible.
Yes.
After listening to a wonderful keynote address by a stalwart in graph theory, Dr. Poornaprajna, we are here to listen to another contribution to mathematics from the region, that is Dr. Sudhakar Ji. Sudhakar Ji, currently Professor and Head of Mathematics Department in Manipal Institute of Technology, Manipal, which comes under MAHE, that is Manipal Academy of Higher Education. Dr. Sudhakar had his Masters in Mathematics from Mangalore University in the year 1986, and he obtained his MPhil in the year 1987. Joining MIT, he did his PhD in graph theory in the year 2000. Since then, he has guided 4 students for their doctoral degree, and currently 2 are working under him. He has published 21 research articles in international journals and has been contributing law in the form of resource person in conferences of national and international level. I am very proud to be one of his classmates in the master's degree and MPhil. A soft-spoken person, but very dedicated and determined person who also likes real life trekking, and his passion in trekking in hills, mountains of Himalayas has made him to do a lot of trekking in the field of mathematics also. So we are very fortunate to have him as a resource person. I welcome Dr. Sudhakar on behalf of Poornaprajna College and on behalf of the organizing secretary of today's conference. Over to Dr. Sudhakar Ji.
Oh, thank you, Professor Raghavendra. He said he is proud to be my classmate, and I am prouder to be his classmate. Professor Poornaprajna said that his talk was very short. Mine is shorter. I have a brief history of what I'm going to talk, and then one definition and one new definition and few results on maybe what is called neighborhood distinct representative graph.
जाना है आज बोर्ड
Yeah.
हाँ
Okay, what we are doing is this. The problem of system of distinct representatives is a classical problem, age-old problem. Maybe defined and somebody did the basic work in the year of 1934 or 35. And it has a lot of applications. To define system of distinct representatives, we consider a set, say W, and a class of subsets of W, say denoted by C, the class denoted by C. We say that the class is representable if there is a function that assigns to each set in the class an element of that set in such a way that no two sets are assigned the same element. Such a representation is called a system of distinct representatives. So first we observe that not every class of sets is representable. For example, if you consider set W to be the set containing two elements A and B, and class of the sets to be C equal to K1, K2, K3, where K1 is the singleton set A, K2 is the singleton set B, and K3 is the set AB, that is set W itself, then obviously the class C is not representable. If we have A as the representative of K1 and B as the representative of K2, obviously there is no representative for the set K3. So obviously it's not true that every class is representable. Then the obvious question is, what is the necessary and sufficient condition for a class to be representable? P. Hall in 1935 gave a necessary and sufficient condition for a class to be representable when the class contains finite number of finite sets. I repeat, it's a finite number of finite sets. Class contains a finite number of finite sets. His necessary and sufficient condition can be given as follows. Let E be a non-empty finite set and C is equal to S1, S2, Sn be a family of non-empty subsets of E. Then C has an SDR, that is system of distinct representatives, if and only if the union of any P of its sets Si contains at least P elements for every P in between 1 and M. So if you take a collection of some, say, P sets and take the union should have at least P elements. If the union has less than P elements, then there is no STR. It looks to be very obvious, but needs a proof. Obviously, I'm not going to prove the theorem. We take the theorem to be true, right? As an example, we take the set E to be containing 6 elements A, B, C, D, E, F, and C is to be the collection of 6 subsets of E, say S1, S2, S3, S4, S5, S6, where S1 contains 3 elements A, D, and C, S2 contains A and B, S3 contains again A, D, and C, S4 is D, C, F, S5 is D, C, E, F, S6 is F. Then A, B, D, C, E, F is an SDR for the collection C. Similarly, A, B, C, D, E, F is another SDR. From the example, we can see that a collection may have many SDRs. So the problem is already dealt. You can think of counting the number of SDRs in terms of size of W and sizes of the sets SI. And it is not true that Hall's theorem is true when the condition of finite and finite are removed, as shown by the following example. For example, let's take W to be the set of natural numbers, say 1, 2, 3, dot, dot, dot. And the collection C to be the collection containing all singleton sets, say set containing 1, set containing 2, set containing 3, dot, 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 and the set N itself. Obviously, this collection has no system of distinct representatives. It has no SDR. If 1 represents the set containing 1, 2 represents the set containing 2, dot, 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 then N has no representative. So this is an infinite collection which contains an infinite set. So Hall's condition is not applicable to this collection. Later in the year 1948, Marshall Hall, M. Hall, showed that P. Hall's condition holds for an infinite collection of finite sets. Even when the collection is infinite, if the sets are finite, P. Hall's condition is satisfied. What we are going to do, or we are going to present here, is a particular question. We take the question of system of distinct representatives to a particular class of subsets. We start with a graph G, obviously finite graph G, with a vertex set V1, V2, Vn. There are n vertices. For every vertex, there is a neighborhood. We take Si to be the neighborhood of the vertex Vi for I is equal to 1 to n. And we consider the collection S1 is to Sn. And we ask the question, when is it true that this collection of subsets has an SDR, system of distinct representatives? Suppose that F has an SDR. Say U1, U2, Un. There are n sets S1, S2, Sn. Each set has a representative and the SDR will be U1, U2, Un, where Ui represents the set Si for I is equal to 1 to n. We can observe that this U1, U2, n set U1, U2, un is nothing but the set V1, V2, Vn, because it is a system of distinct representatives. There are n elements. They are all vertices of the graph G only. Therefore, it must be equal to V of G. Now we define a graph G dash as follows. Vertex set of G dash is nothing but the set U1, U2, Un. In fact, it is nothing but the set V1, V2, Vn, the set of the graph G. And Ui is adjacent to Uj in the graph G dash if one of the following is true. That is either Ui is equal to Vj, or Uj is equal to Vi, or Ui is equal to Vj and Uj equal to Vi. Right? You forget the definition. What we are doing is this. You start with the vertex, say Vi. Vi has a neighborhood, say Si. That Si has a representative. Let it be denoted by Ui. Then make Vi adjacent to Ui. This Ui is same as Vj because the vertex at U1, U2, Un is same as V1, V2, Vn. So Ui is same as some Vj. This Vj has a neighborhood, say Sj. That Sj has a representative, say Uj. Then Ui is made adjacent to Uj. And it goes on. We get a graph, and that graph is called the neighborhood representative graph obtained from the graph G. So that's the definition. So we take a graph G, the vertex set, and we assume that the neighborhoods of the vertices, the class of neighborhoods, has an SDR, has a set of distinct representatives, say U1, U2, Un. And we observe that U1, U2, Un is same as V1, V2, Vn. The set is same as this set. And we define a graph on U1, U2, Un. And adjacency is defined as defined earlier. For example, if you consider the graph G to be the path on 4 vertices, say P4, and Si is equal to Ng of Vi, V1, V2, V4 are shown as in the figure, we can observe that S1 is equal to V2. V2 is the only neighbor of V1. S2 is equal to V1 and V3, 2 neighbors of V2. S3 is equal to V2 and V4, 2 neighbors of V3, and S4 is equal to V3, the only neighbor of V4. Now consider the SDR U1, U2. You can observe that this has an SDR. S1 should be represented by V2 only because it is singleton set. S2 can be represented either by V1 or V3. We take it to be say V3, S2 is equal to V1, S2 represented by V1, S3 is represented by V4, S4 is represented by V3. So the SDR U1, U2, U3, U4 is given by U1 equal to V2, U2 equal to V1, U3 is equal to V4, U4 is equal to V3. Then the graph G dash, according to the adjacencies defined earlier, is union of 2 K2s. U1 and U2 are adjacent to each other, U3 and U4 are adjacent to each other, and there are no other adjacencies. So SDR, that is the SDR graph, the NDR of the neighborhood representative graph of P4 is K2 union K2. As another example, we can take a graph, a bipartite graph with bipartition. Maybe that you can think over before going to the example, you can think over the sizes of the bipartitions. Suppose that the bipartite graph G has bipartition V1, V2. And suppose that we consider the neighborhoods, collection of neighborhoods, and there is an SDR. If you think a little bit more, you can prove that the sizes of the bipartitions must be same. If at all there is an SDR for the class of neighborhoods of vertices of a bipartite graph, then the bipartitions must be of same size. So you can think over it, you can prove on your own, it's very simple. Then suppose that V11, V12, V13, V14 is one bipartite set, and V21, V22, V23, V24 with the other bipartition partite set. Then the neighborhoods according to the graph given can be obtained, and an SDR can be obtained, and the NDR graph, the neighborhood representative graph, can be obtained, and it happens to be the graph given in the figure, and it is nothing but union of 4 K2s. Now you may think that always the neighborhood representative graph is nothing but union of K2s, which is not true, as shown in the next example. For the same bipartite graph given in the previous example, if we take a different SDR, say U1 it to be U11, U12, U13, U14 dot dot dot, U21, U22, U23, U24, where U11 is V22, U12 is V24, U13 is V21, U14 is V23, U21 is V11, U22 is V13, U23 is V14, and U24 is V12. Then the graph, the neighborhood representative graph, contains 2 K2s and 1 C4. as shown in the figure. Now these are some basic observations. What we have observed already is that V of G, vertex set of G, is same as vertex set of G dash. The graph G and its neighborhood representative graph have the same set of vertices. And as we have seen in the definition of adjacency, the vertex is mapped over to or is made adjacent to the representative of its neighborhood. Therefore, every edge of G dash is also an edge of G. Therefore, what we get, V of G is same as V of G dash, and every edge of G dash is an edge of G. Therefore, G dash is a spanning subgraph of G. It's very important to note. G dash is a spanning subgraph of G. And it's also true, or one can easily prove, that every vertex of G dash is of degree either 1 or 2. Because every vertex of G dash is of degree either 1 or 2, every component of G dash is either K2 or a cycle. K2 components correspond to situations where Ui is equal to Vj and Uj is equal to Vi. That is, vertex is mapped over to its representative, and its representative is the same representative is mapped over to back to its same vertex. Ui is Vj and Uj is Vi. In all other situations, that is Vj, Vi is equal to Uj or Vj is equal to Ui, the other side need not be true, then there will be a cyclic movement Ui to Vj, Uj to Vl, Ul to Vk, dot dot dot. Since V of G equal to V of G dash, it has to come back to the starting vertex and we get a cycle. Thus, every component is either a K2 or a cycle. It is very interesting to note, we have a definite name for such spanning subgraphs. A spanning subgraph is called elementary spanning subgraph of a graph G if every component of the subgraph is either K2 or a cycle. This type of spanning subgraphs play an important role in the definition of determinant and permanent of adjacency matrix of the graph. If you refer to the book Graphs and Matrices by Bapat, a clear proof is given, maybe it is proved in many other textbooks, that the determinant of the adjacency matrix can be defined, can be given in terms of the elementary spanning subgraphs. So is the case with the permanent of the adjacency matrix. So the neighborhood representative graph G dash of G obviously is defined only when the collection F has an SDR. If there is no SDR, there is no neighborhood representative graph. For example, if you consider the graph K1N, it is a star with one central vertex and N peripheral vertices. For all the peripheral vertices, neighborhood is a single vertex, that is a central vertex. So if you take the neighborhoods of the peripheral vertices, the size of the union is 1 and number of neighborhoods is more than that. Therefore, P Hall's condition fails and there is no SDR. Right? So it's not true that every graph and the collection of neighborhoods of the graph need to have an SDR. When SDR exists, we define what is the neighborhood representative graph. So in order that the neighborhood representative graph is defined, the collection of neighborhoods of vertices of the graph should have an SDR. Many cases it's not true that they I mean the collection has an SDR. And we have, as we have observed earlier, for in the case of different SDRs you consider, there will be different neighborhood representative graphs. And we can also note that for any connected graph, the neighborhood distinct representative graph G dash, whenever defined, that means whenever there is an SDR, is an elementary spanning subgraph. So we have if there is an elementary spanning subgraph, there is an SDR. Whenever there is an SDR, there is an elementary spanning subgraph. Therefore, we have a theorem which says that a graph G has an SDR. I mean, if you consider graph G with the vertex at V1, V2, Vn, and Si is equal to neighborhood of Vi for I is equal to 1 to n, and F is the collection S1, S2, Sn, then the collection F has an SDR if and only if G has an elementary spanning subgraph. And we can also observe that if corresponding to the K2 components, there is only one SDR defined. Vi mapped over to adjacent to Vj, Vj adjacent to Vi, Vi adjacent to Uj, Uj adjacent to Vi. So the neighborhood of Vi has Uj as representative and neighborhood of Uj has Vi as representative. So the representatives are fixed. And if you consider the cycle component, say V1, V2, Vn is the cycle, or V1, V2, Vr is the cycle, then corresponding to neighborhood of V1, V2 is the representative. Corresponding to V2, V3 is the representative. That is one cyclic way of getting the representatives. Vr, the neighborhood of Vr has V1 as a representative. Or you can trace the cycle in the other direction. For V1, Vr can be taken as a representative. Neighborhood of Vr, Vr minus 1 can be taken as a representative. Dot, 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 you come back to V1. Right? So corresponding to every cycle, there are two ways of getting the representatives of the neighborhoods. Therefore, we have this result. E be a connected graph, V of G is equal to V1, V2, Vn, and H be an elementary spanning subgraph of G. Corresponding to any cycle component of H, there are two ways of getting the part of the SDR, and corresponding to K2 component, there is only one way of getting the SDRs. For example, if you consider, I'm not V1, V2, V3, V4, V5 in one direction or in the anti-clockwise direction, you get different ways of getting the SDR. If you take C6 and these are the possible spanning subgraphs, and corresponding to them, these are the SDRs. So corresponding to this one, there is only one SDR, these are two SDRs, therefore 2 plus 2, totally 4 SDR corresponding to cycles. Right? Now we give a theorem which tells the number of SDRs in a connected graph for the family of neighborhoods of vertices of the graph. It is not a general theorem. It's a particular class of sets which are nothing but neighborhoods of vertices of a given graph G, for which there is an SDR. If there is an SDR, how many SDRs are there is the question. So the number of SDRs is given by this theorem. It states as follows. G be a connected graph and V of G is equal to V1, V2, Vn, and F is equal to S1, S2, Sn with Si is equal to Ng of Vi, I is equal to 1 to n. Then the number of SDRs is given by sigma 2 to the power of C, where the summation is taken over all elementary spanning subgraphs H of G, and C represents number of cycle components of G, which follows obviously by our discussion. We also note the following remarks. If G is a tree, then F has the family of neighborhoods of vertices of G, that is F, standard notation, has at most one SDR, because SDR, number of SDRs is nothing but number of elementary spanning subgraphs. The elementary spanning subgraph cannot have a cycle because it's a tree. Therefore, number of SDRs is equal to number of ways in which the tree can be treated as union of K2s. That is number of 1 factors of the tree. We know that if the tree has odd number of vertices, it has no 1 factor. If it has even number of vertices, it can have at most 1 factor. Right? So whenever the 1 factor exists, that 1 factor corresponds to an SDR. Whenever there is no 1 factor, there is no SDR. Therefore, there is at most 1 SDR for any tree. And obviously, if the tree is odd, there is no SDR. If it is even, it may have 1 SDR. Right? If G is a cycle, then number of SDRs is 4 if n is even and 2 if n is odd, which you can think over and get the answer why it is 4 into 2, right? If G is a complete graph on n vertices, then number of SDRs is dn. It's a very standard notation for number of derangements of n elements, right? All these things can be proved on your own. They are all simple. And there are some simple questions which you can think and work on your own. We can observe that if G is a bipartite graph, then the neighborhood representative graph of G is also bipartite.
presentation
or a cycle. Every cycle is a cycle of the graph G. Since G is even cycles. Therefore, G dash cannot have an odd cycle. G dash has no G dash.
Come on, audience, please. Keep your mics. Only the one who can ask the question should.
So, G dash for a class of bipartite graphs is again a class of bipartite graphs. So, in the class of bipartite graphs, if we take a graph G, its G dash is also in the same class. Now, you can think of all possible different classes where there is a graph G and the neighborhood, the class of neighborhoods have SDR, that has SDRs, and corresponding to the SDRs, we can define the neighborhood representative graphs, and all those graphs are again in the same class. It happens in the case of bipartite graphs, for which other class it happens. You can think over it, right? And as we have seen, we can again think of finding the conditions for existence of S, that is the SDR, such that the representative graph G dash is isomorphic to G. When is it true that there exists a S such that there is a set of representatives such that the neighborhood representative graph of G, that is G dash, is same as G? That also can happen. For cycles, it can happen. For cycles, it is an odd cycle, it is an odd cycle only. Right? So, you can characterize the set S also. The representatives, how to characterize that, and what are the qualities to be satisfied by S such that G dash is isomorphic to G. Like this, many questions arise. If you go through it and think over and try to understand and do it again and again, you can have many open research questions and you can try to answer. And these are the references. And there is a survey article by same person, Miss Kiel, Missy and Perfect, and You can refer the survey article which gives all the results till that date or that time on transversals or SDRs. And you can refer this book, reference 3. It's a very good book for understanding the transversal theory. Thank you.
Thank you, Dr. Sudhakar. It was a very wonderful session. Very interesting topic. I would invite the audience if you have any doubts.
Dear participants, if you have any questions, you can unmute yourself and speak up.
Okay, if there are no questions, I would like to thank Dr. Sudhakar, our sincere gratitude. Well begun is half done. We had two very mind refreshing topics and well prepared, well presented. A good area.
Chat box show participants. Chat in channel meetings is only available to team members.
Have you sent a question there? Akshata Morajikar. Any question?
Chat is disabled.
Okay, thank you, Dr. Sudhakar. On behalf of Poornaprajna College, on behalf of organizing secretary, we really had a very refreshing 2 morning sessions, and many more such events from your side we expect in future also. Thank you.
I would take this opportunity to thank Dr. Sudhakar ji, Professor and Head of Department of Mathematics, MIT. Thank you, sir, for delivering such an informative session. Thank you so much for accepting our invitation. I also thank Dr. Raghavendra, our beloved principal, for chairing the session. Thank you. Again, the feedback link is uploaded in conference site. One can look at it. So we'll begin the next session by 12:15. Thank you. Here is an announcement. We'll have next session by Dr. Pinkimani Goswami, Assistant Professor, Department of Mathematics, University of Science and Technology, Meghalaya. Madam will be discussing on the topic quadratic residues and signed quadratic residues for secure communication. We'll begin the session by 12:15. Stay tuned in.
Madam, I'm not receiving the feedback in the mail. Hello? Hello?
Hello, sir.
Hello?
Hello,
Sir,
sir.
I'm not receiving the feedback. I'm not receiving the feedback link in the my mail.
Sir, feedback link is in our conference site. You can find there.
Conference side, where I can find this conference side? Hello?
It is available in your email, sir. You can check your email.
So there only I'm checking. I'm not getting it that one. I will check again. Okay.
Sir, you can find there. There is a notification bar. You can find it. Thank you.
Welcome, Dr. Sridhar sir.
Thank you. Thank you, Dr. Raghavendra. Good afternoon, madam.
Hello, madam. Yeah, your voice is audible, but can you speak little loud, madam?
Our speaker has some technical issue, so we'll just begin the session within 5 minutes. Sorry for the inconvenience.
Yes, Prasanna, I am joining. Yeah. Yeah. Okay. What you have said? Yes, yes. Now I am comfortable. I don't know whether it is listed. My name is listed there or not. Means I am not sure whether I have joined. Yes. Now I think I have. I can see. Yes, I have joined. Thank you. Good afternoon.
Let us start now. Hello.
Good afternoon. Sir, sorry for the because of the internet problem, I could not join at time.
Greetings to all. I just welcome all the participants back. We have with us Dr. Pinkimani Goswami, Assistant Professor, Department of Mathematics, University of Science and Technology, Meghalaya. As a resource person, ma'am will be speaking on the topic quadratic residues and signed quadratic residues for secure communication. May I request Dr. Sridhar K, Professor and Head Department of Mathematics, KVJ College of Engineering, Sulia, to chair this session. Sir has published several research articles in reputed international journals, main in graph theory. I request Sir to lead the session. Over to you, Sir.
Thank you, Chitra. Good afternoon, everybody. It gives me immense pleasure to introduce our next eminent speaker, Dr. Pinkimani Goswami from University of Science and Technology, Meghalaya. Dr. Pinkimani Goswami has graduated from Guwahati University, Assam in the year 2009 and has completed her master degree in mathematics from Tezpur University, Assam in the year 2011. She has received her doctorate degree in cryptography from the Department of Mathematics, Northeastern University, Shillong, Meghalaya in the year 2017 under the guidance of Dr. Madan Mohan Singh and the co-guidance of Dr. B. Buyan. Currently, she is working as Assistant Professor of Mathematics at University of Science and Technology, Meghalaya. Her research interest area include number theory, graph theory, and cryptography. In the short span of time, she has published 8 research papers in the national and international journals. She is the co-author to the book chapters for the publishers like Springer, APP and CRC publications, and CRC Press, which one is the Taylor and Francis group. About 24 students have completed MSc projects, and at present 2 students are doing their PhD under her guidance. She was the member for the technical program committee for the book Computational Intelligence and its Application in Health Career, which is published by Elsevier in 2020. She is reviewer of the journal Discrete Mathematics Algorithm and Applications, World Scientific Publications. She was awarded as second runner-up of the oral presentation competition on National Meet of Research Scholars in Mathematical Science 2015. This is the brief introduction of Dr. Pinkimani Goswami. Now she is with us to deliver a talk on interesting topic, quadratic residues and sign quadratic receipt for secure communication. I invite you, madam, and share your slides for our online delegates. Welcome.
Thank you, sir, and thank you to the organizing committee also for giving this chance to share my work in front of the research scholars. So thank you so much. So I want to discuss on the topic like quadratic residue and sign quadratic residue in cryptography. So now I just want to share my slide first. So I think I am audible.
Yes, audible.
Okay. So just a minute, I just want to share it. Is it visible? I am sharing.
No, it is not.
I think now you are.
You are unmuted. Unmuted. You.
So is it visible now?
Now it's not visible. Okay, yes.
It's visible? So this is the, so can I start?
Start, madam, start.
So this is the topic, quadratic residue and sign quadratic residue for secure communication. So we know actually that quadratic residue has various applications, not only in the case of security, it has some other application also, like in the field of to check it is how the distributions, how we can check the distribution properties, how means integer factorization problem can be solved. These things where quadratic residue has various wide application in the field of mathematics also and in the real life also. So here I want to show how and why quadratic residue and another concept, sign quadratic residue, can be used for secure communication. So secure communication, basically I will consider here about the cryptography. So I will start with a little introduction with the cryptography. So this is my this is the overview. So I just start with this. So what is a cryptography? So cryptography means it is the study of secret writing. So cryptography actually it is the study of technique for secure communication when in the presence of the third party, which we call actually it is an adversary. So it is actually the science of encrypting and decrypting some messages. So encrypting and decrypting means encrypting means the message is converted to some unreadable format, which is called ciphertext, and decrypting means the ciphertext is converted to again in the readable format. That means we get back the message. So this is the encryption and decrypting process. So in this way, messages are converted to unreadable format, and then we can after the decryption we can able to get the message back. So what is the main purpose of the cryptography? It provides us some security services like confidentiality, authenticity, integrity, and non-repudiation, and all are based on actually mathematics. Without mathematics, we are not able to check this. So what is the confidentiality? Confidentiality means suppose you are sending a message, then this message will be receiver only can read that message. That means authorized party can read the message, but unknown or third party can't. Similarly, there is a concept about the authenticity. Authenticity means you will be able to guarantee that the message was sent by the claim sender only. Similarly, integrity means the message is in between when messages are sending to one person to another person. That in between that message is not modified. That can be guaranteed by cryptography. Then another is the non-repudiation. Non-repudiation means letter sender cannot deny that he did not send the message. He cannot deny the creation of the message. So these are the main aim of the cryptography, and actually cryptography provides this facility. So we have two types of cryptography: symmetric key cryptography and asymmetric key cryptography. So this is the diagram for the symmetric key cryptography. In symmetric key cryptography, encryption and decryption both can be done by the same key. So that means here message and message will be converted to the ciphertext with some key, and the same key will be used to convert the ciphertext to the message. So the main difficulty is here is that sender and receiver, first they have to agree with a key. After that, they can communicate. But this is the drawback here, because if they can meet or they can agree for some key, that means they have to meet each other. Then instead of sending the message, they can instead of agreeing some message, they can directly send a message. So this is the drawbacks for this ecosystem. So next occur the asymmetric cryptography. So here sender and receiver no need to agree with any other key. So they have some one key, public and private key. So here public and private key both are different. So when this is developed by Diffie-Hellman, the idea is developed by Diffie-Hellman in 1976. So here what happened actually, when one person wants to send a message to another person, then that person have to use the public key of the receiver. Okay, and that public key of the receiver and the message, whatever he has, that can be encrypted in this algorithm, encryption algorithm, and this will give you a ciphertext. That ciphertext will be decrypted by the receiver by his private key, and he will get back the message back. So this is the idea about the asymmetric key cryptography. So what cryptography, our focus is this. So this is the well-known and widely used RSA crypto system. It has a various real-life application also. So here the encryption process is this one mathematical equation where M is the message, E is a secret key, E is a private key, sorry, E and N are the private key. With the help of that, this encryption is done. The message is T is the ciphertext of this message, and this message is sent to the receiver. So receiver, what he will do, he will compute the message with the help of his private key, which is his D, P, and Q. So here E and D, they are inverse of each other under modulo phi of. So this is the one well-known and very widely used crypto system, RSA crypto system. So this is the idea about the cryptography. So I just want to go to the main topic. So the next question is, what is a quadratic residue? So what is a quadratic residue? So we know that what is a quadratic residue means, if we have any number, suppose we have considered here it is xi. So xi is a number which is relatively prime to n. Then we call this xi is a quadratic residue if this quadratic congruence has a solution. So x square congruence to xi mod n, if it has a solution, then xi is called quadratic residue. Otherwise, it is called quadratic non-residue. And x is the solution of this equation, which is the x. X is called the square root of xi. So here one simple example is given, considering the n is 13, and we are finding some quadratic residue, and here I am collecting all the quadratic residue. Okay, so here we have 6 quadratic residue under modulo 13, and so we can write like this. So cardinality of this quadratic residue means cardinality of the cardinality of this set is 6. So here, what is QR13? It is the set of all quadratic residue modulo 13. So the main notation is QRN. So the next question is, what is the order of a quadratic residue? What is the cardinality of a quadratic residue? So cardinality of quadratic residue, in particular for this example, when this number is 13 is a prime number, so in this case it is p minus 1 by 2. So it is in general also, if the number is a prime, if n is a prime number, then we used to get the cardinality n as n minus 1 by 2. So if we consider n is p, then it will be p minus 1 by 2. So in general, this is the formula. So if n is any composite number, then cardinality can be calculated by this formula. So this is the cardinality. Now the second question is whether this group, set QRN, it is a group or not. So it is a group. First of all, here I did not prove here. So this is a group. And next question is, it is a cyclic group or not. So the question is, under certain condition, this is a cyclic group. So it should satisfy these properties. Then it is a cyclic group. So the next question is how to find how to check a number is a quadratic residue or not. So how to check it? So answer of this is given by Euler. He has said that xi is a quadratic residue if it is satisfied this equation. So that means to find to check a number is a quadratic residue or not, we just have to calculate this xi to the power p minus 1 by 2. And this has the efficient algorithm here to compute the power modulo. So that is why we can easily check a number is a quadratic residue under modulo p or not. So it has a polynomial time deterministic algorithm. So polynomial time means it is bounded by some polynomial function. Deterministic means any input for the same input you are going to get the same output every time. So this is the complexity of this of the algorithm. So the next question is, instead of p, if we have suppose p to the power k, that means if n is p to the power k, then what will happen? So in that case also, we can say that answer is yes for this question because of this wonderful result that xi is in this xi, it is a quadratic residue under modulo p to the power k if it is a quadratic residue of p and vice versa. So that is why it is easily we can check whether xi is a quadratic residue under modulo p to the power k or not. Here I just want to mention that from here we can easily check whether we can easily find the square root under modulo p to the power k also because of the algorithm given by Hensel. So we can find the quadratic square root also. So the next question is, what about n when n is neither of the two conditions, that p or p to the power k. That means if n is a power of prime. So in that case, this is one nice result we have. This result says that we can say or we can guarantee that xi is a quadratic residue under modulo n if it is a quadratic residue for each of the prime factor of n. So this implies that if we know the prime factor of n, then we can easily check whether xi is a quadratic residue or not under modulo n. But if the factors of n are unknown, then we don't have any formula to find or any algorithm, efficient algorithm to check whether xi is a quadratic residue or not. So finding factorization, it is considered as a hard problem. Till now, number field sieve method is there, which is a faster algorithm till now, but it is not that efficient. We can't find the factor of any composite number by that algorithm. So that is why, since that integer factorization problem is tough, so that is why it is difficult to check whether xi is a quadratic residue under modulo n or not. Integer factorization problem is finding the factors of n, where n is a composite. So because of this, it is difficult to find the square root of n also if n is unknown. If the factors of n are unknown, then it is difficult to find the square root of n also. And by this observation, there are various crypto systems has developed And the first crypto system which is developed by this observation is called the Robin crypto system. Robin has defined it is on 1979. And this is the idea about the Robin crypto system. So encryption process has considered this. T congruence M square mod N, and M the message you have to find with the help of the square root of C under modulo N. And here I just want to mention that for any, if we are prime numbers are of the form 4k plus 3, then we have some algorithm to find the square root of the number. But if P is in general, if it is 4k plus 1 form, then there is no such algorithm, means efficient algorithm is there. So that is why when Robin has defined this crypto system, he has considered P and Q both are of the form 4k plus 3. So this is the Robin crypto system. Now I just want to go to, I want to show you some other result which help us to help us to develop some crypto system based on quadratic residue. So first of all, we have to know what is the legendary symbol. This is the definition of legendary symbol, and we know this. So this, by this definition only, it is clear that as the value of this legendary symbol of this number xi is depend on whether the number is quadratic residue under modulo P or not. And since to check whether a number is quadratic residue modulo P or not, it is efficient. That is why computing the legendary symbol of a number is also efficient. Means we can efficiently we can compute this value. So then we can generalize this to Jacobi symbol. We know these things before also. So this is the Jacobi symbol, this part, and this bracket is not denoted the legendary symbol here. So these are some results. These are some properties of the legendary symbol. That because of these properties, actually, without knowing the factors of n, we can easily find or we can easily compute the legendary symbol of any number, any integer, because of these properties. So now we are defining a set Jn. This set is what? It is contain all those elements of the unit group whose legendary symbol is 1. So if a number has legendary symbol is not 1, that means if that element, that integer is not belongs to this set, then this guarantees that that number, suppose xi is not a quadratic residue. But if the element is belongs to this set, then we cannot guarantee that the element is belongs to element is a quadratic residue under modulo n. Okay? Why? Because suppose the Jacobi symbol of xi is 1, then n has some, suppose it has the prime factor p and q, then xi of t, legendary symbol of xi under modulo p and legendary symbol of xi under modulo q, if both are equal to -1 also, they will gives you 1. So if under modulo p they are -1, that means it does not satisfy the one that xi belongs to xi, this element is belongs to quadratic residue modulo n if xi is a quadratic residue under modulo p or q. So if they are not in that set, then xi cannot be in q or n. So if a element which satisfied that their legendary symbol is 1, this does not guarantee that the element is a quadratic residue. And because of this observation, we can define a new problem here. That problem is called quadratic residuosity problem. This problem says that given this condition xi, which is xi is Zn, that means the legendary symbol of xi is 1, then decide whether xi is a quadratic residue or not. So this problem is called quadratic residuosity problem, and it is considered, it is assumed that this is a infeasible problem. It is not yet solved. So it is assumed it is a stronger, and it is considered that it is a stronger assumption than factoring assumption. So with the help of this, we can construct a crypto system. Actually, Goldwasser and Micali has developed this. This is the first crypto system which is defined on QRP. So it's a very nice observation they have did, that here they have considering. So this key generation process means here public key and private key are generated. So private key is public key is what? It is the composite number n, and PQ, which is the factor of n, are considered as the private key. And then they have considered a number lambda, so whose legendary symbol is 1. So it is a quadratic non-residue whose legendary symbol is 1. So the n and lambda is considered as a public key. Now when someone wants to send a message, so they will send a message with the help of this public key, and receiver will get back the message with the help of the private key P and Q. So this is the encryption process. So how we have to do the message, which first we have to convert it into binary string. So it is in 0101 type of form. So then the sender who wants to send this message to the receiver, he will choose a number xi. This may not be a quadratic residue. Unfortunately, I have considered here also it is a xi. This is any arbitrary number from this unit group. Then he has considered that this value mi will be, if it is 0, then the ciphertext will be considered as xi square mod p. And if mi, this means that this string binary bits are, if it is not 0, that means if it is 1, then he will compute, the ciphertext will be computed with the help of this. So these CIs, this will gives you the ciphertext C. So this is the encryption process. In the decryption process, we have to compute, the receiver have to compute this because he knew what is his private key P and Q, so he can easily compute the legendary symbol of CI. And if this value, so this value, if it is 1, then you will consider the MI as 0, otherwise you will consider it is a 1. So in this way, he can get back the message. So this is the very simple idea of using quadratic reciprocity problem in cryptography. So now I just want to show you some disadvantages here. So what are the disadvantages for using quadratic residue in cryptography? It is basically that we are not, if we don't know the factors of n, we are not able to find we are not able to check a number is a quadratic residue or not. So this is considered as one of the disadvantages for some cases, because in some crypto system, what happened that because we are not able to check whether the number is a quadratic residue or not, so that is why the crypto system can be attacked by indistinguishable Susan ciphertext attack. So indistinguishable Susan ciphertext attack means your adversary has the right to choose his message and he can ask for the ciphertext. So what he can do, he can consider quadratic residue and quadratic non-residue both as his ciphertext and can send to the algorithm, and algorithm will respond according to that, and by the response the adversary may able to reveal some of the secret information, or maybe he can able to find a secret. So this is the disadvantage here, main disadvantage. There are some others also. So this motivates actually to construct the signed quadratic residue group. So that is why now we are going to discuss about the signed quadratic residue group. So before that, we have to know what is the signed group. So if we have, so we know this set, it is the residue set 0 to n minus 1. We can write this set in this form also. Instead of writing 0 to n minus 1, we can start like this also. That means half of the elements are positive, half of the elements are negative. Now, if H is any subgroup of that unit group, then we can construct as new set H plus, which is defined in this way. So, this set H plus contain all those elements, contain the absolute value of the element of H. So, absolute value, why? Because when we have written in this form, we have some negative number also. Under absolute value, it will give the positiveness. So, in that sense, it is considered. So this set is a non-empty set because this is a subgroup. So identity element are always there in that set. So identity element will be in H plus also. So that is why this is a non-empty set. And under this operation, which is defined in equation 1, so this H plus will form a group also. So this is for finding the order of an element of that group. So H plus form a group under this operation. And it has some nice properties. We can define a function from H to H plus by this definition. Then it is a group homomorphism. This function is a group homomorphism. That means it preserves the group operation. And kernel will be either 1 or 1 minus 1 according to the condition whether minus 1 belongs to S or not. And if kernel is 1, then this will be an isomorphism. Isomorphism means it is 1 1 onto function and it preserves group operation. So if it is a 1 1 onto, then in that case, number of element in H and number of element in H plus will be same. Okay? So this in particular, since we know QRN quadratic residue group is a group under the for the unit group. So that is why we can construct the QRN plus also, and this group is defined as sign quadratic residue group, which is denoted as SQR. So it is first application of sign quadratic residue in cryptography, first defined, first proposed in the year 2019 by Hopkins and Kills. So they are the first one who have shown the application in cryptography. So why it can be used in the cryptography? So here, in particular, when we consider n is of this form, n is a product of 2 prime, where p and q are 4k plus 3, then it will satisfy this condition. This will satisfy as a whole also, but under this condition, QRN is a cyclic group. That is why QRN plus is also a cyclic group because the function phi is isomorphism. So number of element in QRN plus and QRN both are same, both are cyclic, and not only that, QRN plus will equal to this set, and this is nothing but all the positive integer of the unit group whose Jacobi symbol is 1. And we know that the Jacobi symbol of a number can be easily calculated. So by the properties number 3 or properties number C, we can guarantee that the element of this sign quadratic residue group can be easily computed. And this helps us to construct some crypto system. So this is the idea that because of this lemma, actually, QRN plus the sign quadratic residue group, it satisfies the properties whatever satisfied by the quadratic residue group. Not only that, we can able to distinguish a number is a sign quadratic residue or not, even if we don't know the number is even if we don't know the factors of the number n. So these are some other properties. So first two properties actually help us to check the unit group is a pseudo-free group or not. So pseudo-free group is a cryptographic group which has various applications. So by the help of this, researcher has proved that the RSA group or unit group is a pseudo-free group when we are sampling the element from this quadratic residue group. And these are some other properties of the quadratic residue. Some are listed here. So these will help us to construct some secure crypto system. So these are not the only properties which I have mentioned. There are various, but just 4 I have mentioned here. So here in together I have defined the sign quadratic residue modulo n square also. N is here as a Blum integer here. So I have defined it like the similar way as I am going to use it for the constructing a crypto system. The same way, but just I want to mention is that for every n, it is not necessary that the group will be a cyclic group or number of elements in that group are same, because it will depend on whether the function is isomorphism or not. So in particular, when we consider n in this way, means PQ form, where P and Q are 4k plus 3 form, then phi is a isomorphism. That is why we can construct like this. And here also, because of this observation, any element of this group can be easily set without knowing the factors of n. So we have the idea about the RSA problem. So here I just want to mention that here we can easily, since we are easily check whether the number is a quadratic residue, sign quadratic residue or not, but we are not, without factoring n, we cannot compute that square root of that. That is why this sign quadratic residue group is considered as a gap group, which is again an important group in cryptography. So these are some definition of some problems based on which are based on cryptography, crypto system, constructing crypto system. Sorry. So here I just want to mention the last one. So last one is you have to find sorry. So you have to find sorry E and lambda only for the given xi, means only xi is given to use, and only the help of the xi you have to find xi and lambda and E, and factors of n are also unknown. So this is called strong SQR RSA problem. Similarly, we can define some problem on Diffie-Hellman also. It means these are the problem we can construct. Some of the problem we can construct here. So this is the Diffie-Hellman problem. Diffie-Hellman means if these x and y are given to you, you have to compute this value. And decisional Diffie-Hellman problem means you have to decide whether you have to distinguish these elements from a random element of sign quadratic residue. So decisional Diffie-Hellman problem is easy, but computational, that this is the computational one. So this problem is hard in case of hard in when the factors of n are unknown, and it is considered that and that is why it is we can say that sign quadratic residue in with respect to this Diffie-Hellman problem also it is a gap. So this is the strong Diffie-Hellman problem. This means here you have to here you have access some decisional Diffie-Hellman oracle. So with the help of that you have to check a number is a you have to check this value is equal to some random value of quadratic residue group or not. So then we are discussing about the partial discrete log problem. This actually I am using to construct the crypto system. This is defined by me. So here we are considering where you have to find an element A under modulo n when h and xi these are given to you. So it is like discrete logarithm problem only. But it is defined on modulo n square. Similarly, we can define decisional Diffie-Hellman problem, the small decisional Diffie-Hellman problem, like same here, but here B is from this range. This is the difference from the computational Diffie-Hellman problem and small Diffie-Hellman small computational Diffie-Hellman problem. Similarly, it is the small decisional Diffie-Hellman problem also we can define. Here also B is considered from this range. And these are some result we have proved that partial discrete log problem over the quadratic residue group under modulo n squared, it is as hard as the partial discrete logarithm problem over quadratic residue group under modulo n squared. And we have proved that we cannot solve partial discrete logarithm problem if we don't know the factorization of n. We have also proved that decisional Diffie-Hellman problem over quadratic residue group is as much as hard as decisional Diffie-Hellman problem over quadratic residue group. Similarly, we are defining for this also that decisional Diffie-Hellman problem it is not it will be hard if factorization of n is unknown. So these are some results we have proved, and these are some other application of quadratic residue, sign quadratic residue in the field of cryptography. It is used in hybrid algorithm. So hybrid algorithm scheme, basically hybrid scheme means here you have using two schemes, means symmetric and asymmetric both cryptosystem. Both the schemes are used. Sometimes the two different crypto system, two different asymmetric crypto system are also used. Here, Elgamal means Elgamal. It is one crypto system here. Elgamal is a public crypto system proposed by Elgamal. So this is a hybrid algamal crypto system. Means in algamal, the asymmetric cryptography is used here. Then there are some twine hybrid algamal crypto system, that key encapsulation mechanism. Then this is proposed by us. Then there is the concept about the self bilinear map. So where also sign quadratic residue group is used to construct a self bilinear map, and this helps to construct some cryptographic primitive. Then I have already mentioned pseudo-free group. It is so by the help of the sign quadratic residue group, it is proved that RSA group will be a pseudo-free group if we sampling the element from the sign quadratic residue. Then there is another concept called static trapdoor DDH group. There also it is used sign quadratic residue group. It is proved that it is a trapdoor DDH group also. These are some properties, extra properties which makes the crypto system more secure. Okay, so these are some application. And this one is because this one, the 4 public key with double decryption mechanism, this is proposed by us. So this is I want to show you. Basically, double decryption mechanism means sometimes what happens. Suppose we have forgot our password. Suppose someone has sent us some message, but we forgot the password. So that is why we are not able to read the message. But what we need that even if we forgot the message, we want to read the message, or we want to get the we want to read that message. So in that case, double decryption mechanism helps. So here 2 decryption processes are there. One is user decryption and another is master decryption process. So here we have generated the key here with the help of the public key, with the help of partial discrete logarithm problem. So this crypto system is based on partial discrete logarithm problem over sign quadratic residue group. These are the public key we have generated. This A is the secret key of the user, and the factor of the N is the master key of the user. And this way we can generate the ciphertext of a message. And this way the user means who have the knowledge about the A, they can get the message back. And if suppose the user forgot the secret key A, then master decryption will help to find the message. Because of what is the key of the master decryption? It is the factorization of M. So whatever message M will be there, we can get back by this also. So this is this is one example of sign quadratic residue, and this is about. So here just I want to conclude that in this lecture, I just want to show you that how this quadratic residue and sign quadratic residue can be used. Here I just want to mention that in case of sign quadratic residue, there are only 2 works are done. It is so there are very much opportunity to work here. So this lecture is to motivate the researchers to work on sign quadratic residue group. So these are some references. Even though I did not mention all the references where quadratic residue, application of quadratic residue are mentioned. Some are used here, and some sign quadratic residue where application of sign quadratic residue is used. So these are some references. So and that's all. Thank you. So thank you. I am done.
Okay, now the time for queries.
Okay.
If any question is there, you can raise. Don't think if you ask question, someone will get angry because all are hungry now. To ask clear your doubt. If any question, please raise your hand.
Hello.
Yes, sir.
Yeah. This one this quadratic residues what you computed. This is even for primes and product of primes you have found. That is it useful if you take power of a prime, so that can this same algorithm be used in using the algorithms in finite fields?
Actually, when you are using power modulo, then it cannot, since we can easily check whether a number is a quadratic residue or not. That is why in cryptography, it has no use. Means we can't use directly because anyone can find it. And factors are also known, because if we write p to the power k, so anyone can knew what will be the factor here. So we can't use for cryptography in case of cryptography, but in other field it may use.
Okay, and this Diffie-Hellman, whatever that algorithm, computations you told, is it only for exchange of keys in a public crypto system, or even it is useful for encryption?
Diffie-Hellman key exchange, actually it is for securely sending the secret key, but with the help of this, the idea, by that idea, actually discrete logarithm problem is defined. And because of the discrete logarithm problem, we can use not directly Diffie-Hellman, we can use the, we can propose some crypto system. But the thing is that we have to consider a group in such a way that where the discrete log problem is hard to solve. So Diffie-Hellman problem is actually basically to sending the secret key. And this idea actually defined, this will help us to develop the field of public key cryptography. So actually the cryptographers are thankful for Diffie-Hellman for constructing that key.
Okay, thank you.
Thank you. I hope I can, you have got your answer.
Yeah. No, but what the original Diffie-Hellman, there also this type of encryptions were computed, or you have used that partial Diffie-Hellman or whatever that later you told, decision Diffie-Hellman. So there we made use of this encryption method, or even in the earlier also that in your original Diffie-Hellman that type of configuration is there.
Okay, I understood. So decisional Diffie-Hellman and computational Diffie-Hellman problem, they actually help us to check the crypto system are secure or not. That is why means they are required. So it is depend on what type of problem you are using in a group. So depending on that, Diffie-Hellman problem maybe means vary, because in case here, in case of partial discrete log problem, we are using quadratic residue group under modulo n square. That is why we are using partial decisional Diffie-Hellman problem. But if you are considering under modulo n, then definition will be little bit changed. Idea are same, definition little bit. But basic idea is that with the help of decisional Diffie-Hellman problem or computational Diffie-Hellman problem, it helps us to check how much a crypto system, that suppose you are constructing a crypto system, then how much it is secure. That is the thing.
Okay, thank you.
Thank you. Any other? So, can I stop sharing this?
Okay, if no more question means, on behalf of all of you, I thank Dr. Pinkimani Goswami for her beautiful and wonderful
thank you
talk on this. Thank you, madam.
Thank you, ma'am. Thank you from college.
Thank you. Thank you,
thank you,
sir. Thank you for advertising. Inviting me for this workshop. And hope researcher or others may get some idea to work on this field. Thank you. So,
fine. I would like to thank Dr. Pinkimani Goswami for accepting our invitation and sharing your knowledge through the session. Thank you, ma'am. Thank you very much.
Thank you.
Also, I would like to thank Dr. Sridhar K for chairing the session. Thank you, sir.
Thank you, madam. Thank you.
Thank you.
Dear participants, feedback link is available in conference site. Please go through it.
So can I leave?
Okay, madam. So I thank Dr. Raghavendra and all the team for the opportunity given to me to chair this person with the eminent speaker. Thank you all.
Thank you.
Here is an announcement. We will have the next session by 2 p.m. The session is about connected induced subgraphs in n-vertex graphs and unicyclic graphs by the eminent speaker Dr. Odes Dozuleri, Assistant Professor, Department of Mathematics, University of Johannesburg, South Africa. We will begin the session by 2 p.m. Also, we will have paper presentation by 3:15 in Google Meet platform. The link is available again in conference site. Thank you.
Thank you. So can I join the presentation given by the resource person method?
Yes, you can join.
Okay, thank you.
Hello. Could you hear me?
Yes, sir.
Great. I think we still have 2 minutes left.
Chaitra madam.
Shall we start?
Good afternoon, all. It's my great pleasure to welcome you all back. We have an eminent speaker, Dr. Odes Dozolori, Assistant Professor, Department of Mathematics, University of Johannesburg, Auckland Park Kingway, Johannesburg, South Africa, as a speaker. Sir will be talking about connected induced subgraphs in n-vertex graphs and unicyclic graphs. May I request Dr. Kishori P. Narayankar, Associate Professor and Chairman, Department of Mathematics, Mangalore University, to chair the session. Ma'am have several publications in international journals, reputed international journals. Ma'am has guided successfully 4 PhD students and presently she is guiding 3. I request Dr. Kishori P. Narayankar to lead the session. Over to you, ma'am.
Thank you, dear. I thank the organizing committee for giving me an opportunity to introduce a speaker, Odes A. Olare. On behalf of the organizing secretary, I welcome you, sir. His present research interests are combinatorics, extremal or structural graph theory, and elementary number theory. He has done his PhD in discrete mathematics from Stellenbosch University under the guidance of Professor Stefan Wagner. He has a structured MSc in mathematical science. He has done his MSc in mathematical science again under the guidance of Professor Stefan Wagner. He has a diploma degree in electrical engineering. He has matricized in pure mathematics, licensed in pure mathematics. He is presently working as an assistant professor in Institut National d'Orly in Benin. He has several awards and scholarships. Few to mention over here are Abin Prize, awarded in 2020. From Mathematical Science of France, NRF Postdoctoral Research Fellowship in 2019 from University of Johannesburg, Faculty of Science PhD Intensive Bursary from Stellenbosch University again. He has awarded a Tech Tribe Volunteer in 2017 from South Africa Innovation Summit, has awarded postgraduate merit bursary in 2017, Stellenbosch University again. Few scholarships to mention over here is Next Einstein Initiative PhD Scholarship in 2016 from African Institute for Mathematical Sciences, South Africa and Stellenbosch University again. Next Einstein Institute MSc Scholarship in 2015 from AIMS again. He has been awarded as Outstanding Member on a Turing Project in 2014. He has been also awarded as a Best Overall Student completing 2 undergraduate programs simultaneously within 3 years. He is also awarded a National Excellence Scholarship for Engineering Studies from 2010 to 15 in Benin. He has participated in several conferences, workshops, and also participated in group discussions. He has a number of publications, several publications into his credit. The most cited publications I would like to mention over here is Indivisibility of DRA Trees, published in 2020 in Discrete Mathematics, and Indivisibility of Topological Trees, published in 2019 in Questionnaires Mathematics. Over to you, sir.
So let me start by thanking every one of you for inviting me to this international conference on discrete mathematics. It is a great pleasure for me to be talking about some of my research topic at this conference. Once again, thank you very much for inviting me. I'm going to share my screen now. So can you see what I'm showing you on the screen now? Hello?
Not yet, sir. Not yet, sir.
So can you see what I'm showing you on the screen?
Not yet, sir.
No.
Not yet. Okay. Let me try more action. Showing full screen. Screen. Can you see it now?
Yes, sir.
Yes.
Oh, thank you very much. So the title of my topic is entitled on connected inducer graphs in graphs and unicyclic graphs. Basically speaking, I'm going to consider a particular problem which consists of counting the number of connected inducer graphs in graphs with a given number of vertices, and also counting the number of inducer graph in unicyclic graph with given number of vertices. Basically speaking, I'm going to consider over a certain type of graphs, those graphs that have the minimum number of connected inducer graphs, and those graphs that have the maximum number of connected inducer graphs, and also characterized by extremal structures. So as you said in your presentation, I'm affiliated with the University of Johannesburg in South Africa, and at the same time affiliated with Institut National de l'Eau in Benin. Let's start with a brief introduction. So I'm considering here only simple graphs. So those are graphs that have no loops, no directed edge, no multi-edges. So by V, I mean the set of all vertices of a graph G, and by E, I mean the set of all edges. So whenever we consider a subset of vertices of a set of vertices of G, and also a subset of edges of a set of edges of G, we get what we call a subgraph of G. Now, if we only consider subset of vertices and all edges incident with vertices in the set H, then we got what we call an induced subgraphs. A graph G is connected if and only there is a path between the two vertices of G. So I'm going to focus mainly on connected induced subgraph of a graph G. So in this talk, I shall determine over certain type of graphs with n vertices, the minimum as well as the maximum number of connected induced subgraphs, and also characterize the external graph structures. To start with, we need to define some basic classes of graphs. By an edgeless graph, we mean any graph with no edge. So there is no edge, so we only have single vertices. However, when there is an edge between every pair of distant vertices in the graph, we get what we call a complete graph. Of course, in the literature, some people use the expression clique, but for me, clique is just a subset of vertices that induce a complete graph, not necessarily the graph. Let's start by noticing the following easiest remark. If we consider all n vertex graphs, obviously, the edgeless graph has a minimum number of subgraphs, not necessarily connected subgraph or induced subgraph, but subgraph in general, while the maximum number of subgraphs is uniquely attained by the complete graph. How can we see this? By definition, there is an edge between a pair of vertices in a complete graph. Therefore, the complete graph has the maximum number of subgraphs. Now, when we remove all edges from a graph, we get the edgeless graph, which means that the edgeless graph has a minimum number of subgraphs. So we are able to characterize number of subgraphs in terms of minimum and maximum. So what about number of connected induced subgraph, or maybe what about the number of connected induced subgraphs? Let's remark again that now if we consider rather the number of connected subgraph, then the edgeless graph as well as the complete graph, they all remain extremal graphs. The remark is that all connected subgraphs of connected induced subgraph actually the building block to obtaining the all subgraph in a graph G. So when we consider connected subgraph, they still remain extremal because all subgraph that we obtain from Kn, their connected their building block are again connected, are again complete graphs, so they are also connected. But in the empty graph, I mean in the edgeless graph, there's no edge. Therefore, all subgraph that we got there, they are all always connected, since they are all single vertices. So this quickly allows us to write down a formula for the number of connected induced subgraphs in the edgeless graph, which should obviously be n, if n is the number of vertices. And the complete graph, this should be 2 to the power n minus 1. All subset of vertices, excluding the empty sets. So why are we studying topics like this? I'm enumerating here some work that are related to what I'm doing. Titman and collaborators of him, they enumerated the number of connected components in induced subgraph using a generating function approach. What happened is that they consider induced subgraph not necessarily connected. So we all know that when we consider induced subgraphs, those graphs might have several components. A connected component, a component for short, it is just a maximal subgraph that is connected. So they were interested in finding the number of connected components in any induced subgraph. Their approach relies heavily on the generating function. So when they use generating function to encode the structure of graph. Around the same time, Yang and Ye, they also gave a linear time algorithm for counting the sum of weights of subtrees. Subtrees are just a particular graph of graphs. When we consider we are not interested in cycle in a graph. we get what we call a tree. A tree is just a connected acyclic graph. In their paper, they also asked for methods for enumerated connected subgraph of a connected graph. That was my primary motivation to study this topic. Since in this paper, in the paper by Yang Ye, they asked for methods to enumerate connected subgraph of a connected graph. So instead of enumerating connected subgraph, I realized that we can actually enumerate connected induced subgraphs. Of course, from induced subgraph, we can remove edges in such a way that we still get connected subgraph. So induced subgraph as a building block for obtaining connected subgraph in general. Recently, Crocker and collaborators of him, they also investigated extremal structures for what we call the mean order. What do we mean by mean order? They look at the all connected induced subgraph in a graph G, and they count the order of every subgraph, take the sum and divide by the number of subgraph. So we roughly speaking get we call the mean order of a connected induced subgraph. But they did not consider connected induced subgraph in graph in general, but they restricted themselves to what we call co-graph. Those are just graphs that contain no 4 vertex induced parts. So in many applications, one is also interested in counting subgraph of fixed order K. Not only all connected induced subgraph, or subgraph or subgraph of fixed cardinality, and this appears, for instance, in many fixed cardinality optimization problems. I'm going to give you references at the end of this talk. Recently, again, some researcher, they designed algorithm for enumerating all K vertex connected induced subgraph of G. So I immediately get from this literature 2 main motivations. Can we count connected induced subgraph in connected graph, or can we maybe count connected induced sub of fixed size? By size, I just mean the order here. Though some people refer to size as the number of edges in the graph. There are in literature several work related to connected induced subgraph. However, what we know in the literature, most of the papers that appear in the literature, they all focus on trees. For instance, Zikeli and Wang, they prove that if we consider all unvertex trees, then the path minimizes the number of subtrees, while the star graph maximizes the number of subtrees. A star is just one vertex with several leaves attached to it, while a path is just, it's a succession of vertices and edges. They also prove that if we consider fixed cardinality, then the path also minimizes the number of K-vertex subtrees. So the number of subtrees, we started with a paper by Sekeli and Wang in 2005. There quickly appear in the literature various categories of trees. For instance, we can find many applications of counting number of subtrees in phylogenetic reconstruction. So as I just said, most of the existing work will be limited to various class of trees, or maybe tree-like structures, such as unicyclic graph. What do you mean by unicyclic graph? It's just add one edge between 2 non-adjacent vertices in the tree, and you get precisely one cycle, what we call unicyclic graph. Of course, we have bicyclic graph, tricyclic graph, and so forth. But from bicyclic graph, it's already become very difficult because there are different ways of embedding edges in the graph. So many natural generalization arises, as I said. Maybe we can say, let's work on this topic, extremal graph structures with respect to the number of subtrees. So instead of counting the number of subtrees in trees, we may be interested in counting the number of subtrees in graph in general. Also, we can count the number of subtrees, subgraph, for instance, or any subgraph in graph in general, or maybe counting the number of connected subgraph containing a particular vertex. This also is a topic of wide interest in the literature, especially in extremal graph theory. For my talk, I shall mainly focus on the number of connected induced subgraph of a graph or unicyclic graph, but instead of just giving orders, which I already presented a result in my previous slides, I'm going to prescribe also what we call the number of cat vertices in the graph. Cat vertices are just those vertices in a graph which will move on from a graph, disconnect the graph. Or if you are considering graph in general that are not necessarily connected, when you remove those vertices from a graph, you strictly increase the number of connected components. So some notation as in order, by n key G, I'm going to mean the number of K vertex connected in this subgraph. And for abbreviation, let me just CIS for short. And by NG, I'm going to sum this quantity over all possible value of K. So if we are looking for one vertex connected in this subgraph, then this is obviously the number of vertices in the graph. If you are looking for two vertex connected subgraph, this is just the number of edges in the graph. If you are looking for the number of subgraph with precisely n vertices, this is just one, which is the whole graph itself. But if you are looking for n minus 1 connected in these subgraphs, then this cannot be more than the number of vertices in your graph, because we just need to remove successively remove one vertex from the graph. Of course, some might be disconnected and some are still connected. That's why you have this upper bound. But we are going to be more precise in the following slides. Our basic results read as follow. If we are given a graph G with order n, then obviously we already proved this, that the minimum number is equal to n, while the maximum number is equal to 2 to the power minus 1. We have left equality if we are dealing with edgeless graph, and we have right equality if and only if we are dealing with complete graph. Recall this inequality from the previous slides. I can even be more precise. So I already know what a cat vertex in graph in G is. Then the number n minus 1 connected in this subgraph in G is precisely the number of non-cat vertices in the graph. So a cat vertex, as I say, is a vertex whose deletion around that G disconnected. So the number n minus 1 connected in this subgraph is precisely the number of non-cat vertices in the graph G. Similarly, if you have considered two vertices connected in this subgraph in the graph G, then this is at least n minus 1, because we know that when a graph is connected, we can repeatedly remove edges from a graph to get a tree. But tree only have n minus 1 edges if you have it has n vertices. And this is a very well-known result, basic result in graph theory. So let's start with our main interesting part of the talk. The first theorem reads as follows. If we consider all connected graph with order n, then if we are looking for, or if you are maybe interested in counting only k vertices connected in this subgraph, then the part realize the minimum number connected in this subgraph. And this number is given by n minus k plus 1. I'm going to give you a flair of how we can prove this result, although it's not that difficult. So assume that G consider a connected graph of order n, and we assume that it's not isomorphic to the part. So there are two cases to consider here. First of all, if our graph is isomorphic to a cycle, then we all know that when we remove an edge from a cycle, we get a part graph. But then that edge E that was removed from a cycle, if we fix that edge in the cycle, then we can get any connected in this subgraph that contain that edge, since we are only dealing with at least two vertices connected in this subgraph. So this means that the number connected in this subgraph of order K in G is statistically greater than the number connected in this subgraph of order K in the part Pn. So we prove our theorem in the case where G is isomorphic to a cycle. If G is not isomorphic to a cycle, then we know that every connected graph has at least a spanning tree. A spanning tree obtained by just removing, in a clever way, some edges from a graph G to get a tree. So a spanning tree is just a tree that contains all vertices of the original graph. But since we already remove edges from a graph, the number of connected graph in the graph G is at least the number connected in this graph in the tree T. We have equality if only G itself is a tree. But then we already proved from a result by Zekelian Wang that the part has the minimum number of k vertices connected in this subgraph. In this particular case, the minimum number of k vertices of tree. So we have strict inequality. And this is just by basic counting argument. But now when you sum this quantity over all possible value of k, you get n plus 1 choose 2, which is the total number of connected in this subgraph in the part, or maybe it's the total number of subtrees in the part graph. Let's move on. Now let's look at what happened from the maximum number connected in this subgraph. Here we can prove that there is no single class of graphs that realize the maximum number of k vertices connected in this subgraph. We actually have a rich class of graphs. Let's start by giving some definition. Recall that I told you in my previous slides that if I'm looking for the number n minus 1 connected in this subgraph in the graph G, I just need to remove those non-cut vertices from a graph. If I don't do that, obviously by removing any vertex from a graph, I'm going to get at most n connected inducer graph that all have n minus 1 vertices. So those graphs with a property that whatever vertex you remove still give you a connected graph, they are called two connected graph in the literature. Example includes cycle. If you remove any vertex from a cycle, you still get a connected graph, but more precisely a path. If you remove any vertex from a complete graph, you still get a complete graph which is connected. So those are just two particular classes of what we call two connected graph. So I'm going to have to show that if I denote by G, Ln the set of all non-isomorphic graphs that we obtain by just removing independent. What do you mean by independent edge? You are giving me, I'm given, for instance, a graph G, and then I look into the graph and look for two edges that do not share any common vertex. If you remove, they are called independent edges. So if you remove any set of independent edges from a complete graph, it's not difficult to see that you still get a connected graph. But since we are not dealing with two vertex connected inducer graphs, since we already dealt with those cases in my previous slide, then it's easy to show that all graphs taken from the set GLN, they all realize the maximum number of k vertex connected inducer graph, which is just the number of subsets of vertices with k elements, which is n choose k. Equality holds for all such graphs. Of course, the restriction on L is that since we are dealing with independent edges, the number of independent edges cannot be more than half times the number of edges in the graph. This is most obvious. Since we are only considering independence, we need to talk about at least two edges in the graph. Now, the most important part of the talk, which I also realize, things become more difficult if now one restrict ourselves to n vertex unicyclic graphs. In my previous slides, we already presented results regarding the number of subgraph or the number of connected subgraph or the number of connected induced subgraph in unicyclic graph, in for instance, in connected induced subgraph. Now, what do we mean by unicyclic graph? I defined previously, it's just a graph that contains exactly one cycle. If you look at the online encyclopedia or integer sequences under this number, you soon quickly realize that the number of unicyclic of any fixed order grows quickly like this. So it's obviously not possible to count all subgraph, all connected, all unicyclic graph, to count all of them, take particular graph and count the number of subgraph and look at the minimum and the maximum. However, in STMO graph theory, we usually use tools such as finding graph operations or graph transformation that can increase the invariant we are looking for while preserving the graph structure. This is basically most of the ideas that I'm going to present in this part of the talk. I'll start by defining two particular graph of graphs. If I consider the cycle for order 3, or which is also a complete graph of order 3, and then by it I defining one end of a path graph with one vertex of a complete graph order 3, then I got what I am going to call here G3n minus 3. Now, if I consider the star graph and join two non-adjacent vertices, which means two leaves by an edge, I'm going to get what I just call here Qn. So we prove that this graph, which is G3n minus 3, it is the unicyclic graph of order n with the smallest number of connected inducer graph, while Qn is the unicyclic graph of order n with the greatest number of connected. I mean, for me, this should not be much surprising, given that it's already known in the literature that the path graph realizes the minimum number of sub-3 and the star graph realizes the maximum number of sub-3. So if we just add one edge in the star graph, one might hope that the resulting graph may have the greatest number of connected inducer graph. And when we consider a long path and add an edge in a clever way, one must hope that the resulting graph may have a minimum number of connected inducer graph. This in this case, we are going to give ideas on how to prove these results. Our preliminary results start as follows. First of all, we try to count the number of connected tensors in a cycle graph using basic counting arguments, and that gives you this result. If you want to see what happened here, you see, if you consider the cycle graph, then you have V0, V1, V2 up to Vn. Vn is just nothing but V0. See, this is just a cycle. So if you consider a subset of k elements of a vector set of Cn, and you want to get a inducer graph, then this means that you can just take a circular way. In a circular way, just take some consecutive vertices like this, and then you get a connected. They are all part, actually. They are all part. Unless the starting vertex, which is I call it Vj here, is just the same thing at the end vertex here. But this representation fails to be unique if and only if k is equal to n. So this means that for every other k between 1 and n minus 1, we have precisely n connected inducer graph of every other k. But when you consider k is equal 1, this is just with some graph Cn itself. So we have n times n minus 1 plus 1, and that gives us n squared minus n plus 1. This is just a basic idea around the proof. But that's just a lemma. We still need one more lemma, actually two more lemma. Recall that I consider the cycle of order 3 and the long part attached to it. Now I'm interested to generalize that graph. Let's consider a cycle of order here, P, a long part attached to it. I'm going to call it tadpole graph because this graph is known to be extremal for many other types of invariants in the literature. For instance, with spectral radius, the number of vertex independent set, the number of edge independent set, there are many graph invariant literature for which this graph is known to be extremal. So people usually use the name tadpole graph to refer to it. So one can prove using basic counting arguments that the tadpole graph, its total number of connected inducer is given by this formula. And if you want to do this, what we do is that we count some graph that contain this particular vertex V0, which it has to contain all parts as this, and connect and do some graph that contain this particular in this block, for instance. And that's how we get this formula. I'm going to give a proof on this formula since the main idea of a talk is not to give in several proofs, but this present result that has been useful in literature. So I still need more following lemma about trees. This result is well known in the literature is that if we are considering the number of subtrees that contain the roots of a root tree T, then this is at least the order of a tree, and the graph of a tree that are realized that bound is nothing but just a path graph. But you see here what's happening. The path graph is known to be extremal for many instances. You see, it's not only minimizes the number of subtrees, or number of k-vertex subtree, but it's also minimizes the total number of subtrees, and it also has a minimum number of subtrees that contain the roots. Of course, we have to root the path at one of its ends, and the proof goes as follows. Assume that T is a tree with root V. Therefore, we know that in a tree, there is a unique path between the two vertices. So if I fix any vertex U from a tree, then I consider the unique path that joins V to U. And this path is the subtree of tree, which means that we have at least n subtrees if that contain a particular vertex V, if n is the order of tree. But let's prove that this actually is straight if T is not a path. If T is not a part of T is a part, but V is not its leaf of T, then we know that since what we count here, they are all parts. So if T is not a part, then we have straight inequality. But if T is a part, but V not a leaf, then the T itself was not one of the n subtree counted before. That's how we get straight inequality. This lemma 8 is going to be very useful. So now we can present our main results on unicyclic graphs. We start with the minimum number of connected inducer graph. The theorem says the following. If G is a unicyclic graph of the at least 3, then the number of connected inducer graph G is at least n squared plus 3n minus 4 divided by 2. The bound is reached if and only if G is the graph that defined before, which is just a cycle of order 3 with a long path attached to it. The proof goes by induction on the number of order of a graph G. Here's the sketch. By our lemma 7 previously, we already got a formula for NPQ. In particular, when I replace P with 3, I get a formula for NG3N, which can be written as follows. So when we replace N with 3, you see that the statement holds. Since you get exactly 7, because in the case where N is equal to 3, this graph is just a cycle of order 3. But we can show easily, this is just a basic mathematics, that we already know from a lemma of a number of connected of cycles given by this, and this is strictly greater than that. So this means that provided n is greater than 3. So our statement holds for the base case of induction is n equal to 3, and this is clearly seen to be true. Now we assume that we have a graph G which is not a cycle. Of course, if it is not a cycle, that means that since it's a unicyclic graph which is not a cycle, it has at least one pendant vertex. If there's no pendant vertex, then the graph is cycle. But we already remove a case where the graph is cycle. So let's fix a pendant vertex, which is also called a leaf if you want. So leaves are usually used for trees, but I mean we can also use leaf or pendant vertex when we are dealing with graph. So when I fix a particular vertex V in my graph G, and I remove that vertex from G, I still get a unicyclic graph, since V is a pendant vertex by definition. But now I'm getting a unicyclic graph or order one less than order of G, which means that I can use the induction on N to prove that the number connected in this circle is at least the bound that we are looking for. I'm going to give more data about this proof, but just know that it's possible to prove it by induction. You want just need to apply the induction hypothesis to G minus V and then add those connected subgraph that contain the pendant vertex G. That's why I put just thoughts here. This is the sketch of the proof. Now, what about the maximum number of connected in this subgraph? This becomes more difficult, but it's tractable since we were able to characterize graph in this case. So recall that what I mean by QN in the previous slides is just we take a star graph and add one edge between two leaves. We can see that graph contains only one cycle, which length is 3, so it's a unicyclic graph. Our main result is that follow. If G is a unicyclic graph of order greater than 5, then the maximum number of connected induction graph is equal to n plus 2 to the power n minus 1. We get equality if and only if our graph G is isomorphic to the graph Qn that I just defined before. So again here, I'm going to give ideas of how we prove this. So why did we remove the starting values of n, namely n is equal to 1, 2, 3, 4, 5? The remark is that if you are considering Q4, you just get the gap that minimizes the number of connected inducer graph. That's why we are removing the case where n is equal to 4. Of course, we still have a cycle, but we already compare all of this in the previous slide. Now, for n is equal to 5, we check that we only have three unicyclic graph with 5 vertices, namely the cycle, the graph Q that I just defined before, and the so-called banana graph. Banana graph, because this name is also well known in the literature, it's just a graph that you obtain by attaching a pendant edge to a vertex of C4. You just consider the cycle of 4 vertices and attach a pendant edge. Then, though all those graphs have the same number of connectors, namely 21. So we have, in the case where n is equal to 5, we have 3 graphs that realize the upper bound. Now that's why I see I'm going to characterize graph here. I just remove the case when it's equal to 4 and 5. So in order to prove this theorem, we need to present some intermediate results. For instance, we need to present the counterpart of lemma 8. Recall that in lemma 8, we proved that if we are considering subgraph or subtrees that contain a root of a tree, then the minimum is attained by the path graph. But here, if we are looking for a root tree again, which root is V, then the number of subgraph, or if you like, so subtrees, if we are dealing with trees, that contain V and has the maximum number of subtrees is only obtained when we are dealing with star graph, and V is the center of a star graph. Here's the proof. Of course, if you consider the star graph, V is its root, then any subset of leaves that contain V always induce a star graph, which is connected. So there are only 2 to the power n minus 1 subset of vertices of 3 that contain the roots, which means that the number of subtrees that contain the root cannot be greater than 2 to the power n minus 1. Now, if we have a star graph whose center is V, then all such subsets induce a connected subgraph. Otherwise, which means we don't have a star graph, which means the root. Then there is a vertex which are distance at least 2 from the roots, because all the leaves are at distance at 1, precisely 1 from the roots. In this case, if you consider that vertex in the roots, you do not get an induced subgraph, which means you have state inequality. Now, we also need to know what happened regarding the set of all connected induced subgraph of a Banach graph. Again, this is a basic counting argument, and we can prove that the number of connected induced subgraph of the Banach graph is given by this quantity. I'm not going to give a proof, but then to finish off with all intermediate results, we need to present proposition 13 here. This says the following: if you are given a root 3 T, whose root is V, and L is a leaf of a tree, then the number of subtree that contain both, it has to contain the roots, which is V, and it has to contain that leaf, which is L. Then the number of subtree that contain both vertices in the graph is at most 2 to the power n minus 2. And equality holds if you only T is the star and V is the center. The proof goes the same way. If one already know something about subtrees in trees results, many papers by Sekeli and Wang, then we should realize that this proposition 13 actually parallels what Sekeli and Wang already proved in their paper 7. Because they show that the star maximizes the number of subtrees that contain at least one leaf among all trees of a given order. So this proposition 9 just come to confirm what you already know, but actually try to generalize everything from containing at least one vertex, one leaf, to containing both one leaf and the root of a tree. Now, we are now able to give a proof sketch of a theorem 10, which is all about counting the maximum number of connected induced subgraph. So let's start. Remember that the Banach graph is just a cycle of order 4 with a star graph like this. And our graph Qn is just the cycle of order graph with a star graph like this. We can prove, I'm going to prove it, it's just a result I need it. We can prove that if you want to count connected induced subgraph that contain this particular vertex V, which is like a heart of a graph, then this is just 2 to the power n minus 1. On the other hand, if you remove V from Qn, what do we get if you remove V from Qn? If you remove V, then we get here, we get only n minus 3 single vertices, and we get one edge, 2 vertices joined by an edge. Then we can count the number of subtree there, and that's just because we get, as I say, n minus 3 copy of single vertices, and only 1 copy of a part of order 2. So this means that the number of subgraph connected in this subgraph that do not contain that particular vertex V is equal to n. And now if we count the number of subgraph, as I say, that contain VC 2 to the power n minus 1, adding them up, give us the total number of connected in this subgraph in this graph Qn. However, remember that our lemma 12 shows that we already know from lemma 12, we already have a number of subgraph in the Banach graph. And this is just basic mathematics that if we can prove, we can prove that this quantity on the left-hand side here is 30 less than this quantity on the right-hand side, provided that n is greater than 5. So you see that if you are looking for, if we want to count maximum, if we are looking for the maximum subgraph, number of subgraph, then we just remove all Banach graph from our set of graphs, our set of candidates or potential candidates. This is what we do in the following. If G is a graph having the maximum number connected in this subgraph, then we can assume that G is not Banach, because we already proved that it's not Banach, because Banach is strictly less than something which is Qn. So it cannot be Banach graph. And since it's not a Banach graph, I'm going to consider the unique cycle in the graph, which I call CK. Then it's easy to see that any unicyclic graph has the shape depicted in figure 3. Here's the figure 3. So you have your cycle, which is the only one cycle you have in your graph, and all these three are just trees, root trees, rooted at this vertex V0, V1, V2, up to Vk minus 1. This is the general shape of a unicyclic graph. Now, in my proof, I'm going to restrict notations. So the number of vertices in those three, I'm going to call it set it Nj. If I do this, I'm not going to give a proof of course, but I'm going to give ideas. Our first step to proving this theorem is to show, we first prove that for all G, the 3T has to be a star graph with center Vj. If it is to maximize the number of connected inducer graph. This is the very first step to proving the theorem that every tree TG has to be a star graph with center VG. Next, after proving this, remember that we have KT attached to the cycle. But we prove, our next step, we prove that if this graph has to maximize the number of subtree, then we cannot have, we should have at most 3, which means exactly 3. Because the cycle has the order, if we speak of cycle, then the order for unique cycle has to be at least 3. So after proving claim 1, we now prove that K must be equal to 3. Now, if K is equal to 3, we need to know what happened for the order of all these 3 trees that are attached to the cycle. We prove that two of the 3 trees attached to the cycle must only be single vertices. You see, if I combine all these 3 claims, then I get the cycle of order 3 with only one star graph attached to it. The center of the star graph has to be identified with one vertex of the cycle. And this is precisely the graph that I defined previously. So this completes the proof of the theorem. Of course, proving claim 1, claim 2, and claim 2, it's a bit involving, but it's doable. Just bring some more structure in graph, and we are able to prove it. So I think I have said much in this talk. Let me see, I still have 5 or 10 minutes left, something like that. So let me conclude this talk by recalling that I started by showing that the path graph not only realize the minimum number of connected inducer graph among all connected graph, but it also remains extremal when we are dealing with k-vertex connected inducer graph. This is our first remark when I started with this talk. So we also proved in the talk that if we are interested in the maximum number of k-vertex connected inducer graph among all connected graph for order n, then we do not have one single class of graphs that reach the bound, but we still have many class of graphs. And how did I obtain them? I only consider the complete graph and remove independent edges from a complete graph. Of course, that's the reason why we remove the cases where k is equal to 1 or k is equal to 2 or k is equal to n. Though, when I was about to finish the talk, I mainly focused on unicyclic graph, the family of unicyclic graph for order n. So for those graph, what I prove is that I will prove that the minimum number of connected inducer graph is uniquely attained by the tadpole graph. What do you mean tadpole graph? We just consider the cycle of order 3 and attach a path to it. We identify one end of the path with one vertex of the cycle. But for the maximum, I just consider the star graph and add one edge between two leaves of the star graph. That's how we get the structure, the graph structure that maximizes the number of connected. Of course, as I mentioned in my talk at the beginning of the time, I say I also want to consider graph of order n a number of cat vertices, but I soon realized that if I add this part to talk, then I'm going to spend more than the time slot that is allocated to me. So maybe I will have a opportunity, maybe in later stages, to present results on the number of connected inducer graph of order n in a given number of cat vertices. They are reading the literature, and we have several papers that talk about this topic actually. So, for further questions, many natural questions arises because of this talk. For instance, remember we said that path has a minimum several times. But then in the path, all vertices have degree 2 except the end. So what if we do not want to deal with graphs that have vertices of degree 2? Those are called connected series reduced graph or homomorphically reducible graph or topological graphs in the literature. So this is also a topic of natural interest. Count what are the graphs having the minimum number of connected inducer graph among all connected series reduced graph of order n. Of course, to be honest with myself, I have not given a thought to this question before. But I think it's doable. It might get very hard, but it's doable. The second question that arises is the following. Can we find a constructive characterization of a graph extremizing the number of connected induced graph of all graphs with prescribed order in number cycle? Remember, when the number cycle is 0, we have 3 graphs. When the number cycle is only 1, we have unicyclic graph. I already dealt in my talk with a case where d is equal to 0 and d is equal to 1. But what about d is equal to 2? What about d is equal to 3? What about d is equal to 4? Myself, I have been trying to give thoughts to this question, but I soon realized that even in the easiest case where d is equal to 2, there are several ways for the cycle to intersect. You see what I'm saying? This problem can appear out of reach due to the various ways in which the cycle may intersect. Maybe special case of bicyclic graph, d is equal to t or 3, because even for d is equal to 3, we can have the bicyclic graph. Those are still of interest. Let me tell you that in the literature, there are results on the number of sub-tree or bicyclic graph, but not yet on the number of connected induced graph in bicyclic graph. And the case d is equal to 0 is 3, d is equal to 1 is has been already treated in this talk. So I think that's just all I want to share with you. And for references, I might refer to a similar paper by Jamison in 1983 on the average number of nodes in a subtree of 3. One can also look at a paper by these researchers that design a new algorithm for finding network motifs which are noting budget number of subgraphs that are isomorphic to a particular graph structure. There are also papers on enumerating the number of connected induced subgraph. Those are just all of these papers have algorithm flavor. Okay, that is algorithm for counting. They are not really doing estimate graph structure, but they are doing their design algorithm to count. There might be linear subtype exploration algorithm or something like that. Again, there is a paper by this guy, an algorithmic framework for fixed coordinality. As I told you in the beginning, people are also interested in fixed coordinality optimization from those are here they consider sparse graph and they apply to dense graph problems. And there is a paper, recent paper in 2018 by Lucas Small on the mean connected induced graph order. Co-graph are just graph with no induced 4-vertex paths. And there is also a paper on more on connectedness graph and graph polynomials. Of course, there are several papers. For example, paper by myself, Stefan Wagner, and Eric Andresiana, with several researchers, of course. So I'm not going to enumerate them here. So it's always good to give credit to other people who have done his own work. Okay. Thank you very much for your attention.
Thank you, sir. Thank you for your wonderful talk. The session is open for discussions. Any questions? The session is open for discussions. Any questions? If not, then may I, sir? Odyssey? Professor Odyssey?
Okay.
Am I audible?
So, are there any questions so far?
If not from the audience, then may I?
Okay, if not, I think this is just the end of my presentation.
One from my side, sir. Professor Odyssey?
Yes.
You have discussed something on connected induced subgraph in n-vertex graphs and unicyclic graphs.
Okay. Yes.
This induced subgraphs, does it have any property? Or just collection of?
Sorry, say again, I can't hear you.
Am I audible, sir?
Yes, I'm listening to you now.
Yes, sir. You have given a talk on connected induced subgraph in n-vertex graphs and unicyclic graphs. Those induced subgraphs, whatever you are collecting, is it with any property P?
Here, I mostly focus on induced subgraph as you just realize it, because we know that all subgraphs can be obtained from induced subgraph, because you first need to find an induced subgraph of if you are given a subset of vertices in graph, then there is only one connect inducer graph that contains all the vertices, because it has to contain all edges into the incident with that vertex in the set. So you repeatedly remove edges from that inducer graph to get all connected, all subgraphs. But of course,
the only property is connectedness.
Yeah, there are several properties, for instance, of being connected. If you consider inducer graph, some might be connected, some might not be connected.
Yeah.
But if you want to count all subgraphs, I think that is just easy. All subgraph just means that counting all inducer graph and all subgraph that you can obtain by removing edges. The problem becomes more interesting if you restrict yourself to connected subgraph. Maybe connected subgraph or connected inducer graphs. But subgraph in general.
Also add one property, sir. Along with connected,
properties.
You can also add one more property.
Other properties?
The property may be any, sir. It may be Eulerian, it may be Hamiltonian, it may be self-centered, it may be anything. Along with connected graphs, the property may be anything. So that could be.
Yeah, I mean, okay. Yes. For instance, recently, a friend of mine and myself, we consider what we call we try to find bounds on both the sum of a number of connected graph of graph G and its complements, which is another Gaussian inequalities, for instance. Yeah, it's also possible to consider some connected graph of order n with other parameters. For instance, the margin number. For instance, even myself, I started working on this. I have some drafts already available, but I'm yet to finalize the work. We can consider many parameters in the graph, not only cat vectors.
Yes, sir. Yes, sir. Thank you for your wonderful talk. Any questions from audience? If there are no questions, then let me thank Professor Odyssey. Thank you so much for your wonderful talk, sir.
It is a pleasure.
Yeah. I thank the organizers for giving me an opportunity to welcome Professor Odyssey. Thank you, sir.
Thank you very much.
Over to the organizers.
I would like to conclude the session by thanking Dr. Rhodes A.V. Dozzolari for making time and having such an informative session. Thank you, sir. Also, I would like to thank our chairman, Dr. Kishori P. Narayankar, for chairing the session. Thank you, madam.
Thank you, ma'am. Thank you.
We will have the paper presentation by 3:15. I request paper presenters to join through the respective links, which is already there in the conference site. Thank you.
Yes, thank you, ma'am.
Okay, feedback link is in conference site, so you can give the feedback through that link. Thank you.
By this, Hello.
Good afternoon, everyone. All have come. Mr. Purushottam.
No, sir. Jyotiraj is missing.
Then Stalin Kumar.
Stalin Kumar present.
Yeah. Then Muhammad Sadiq.
Yes, sir.
Okay. Jyotiraj.
Good afternoon, all present here. I would like to welcome you all to the paper presentation
Jyotiraj.
session of the conference.
Jyotiraj is
We
not
have
here.
with us Dr. Pradeep B. Bhatt, as chairperson of this paper presentation session. It's my privilege to introduce him to the audience.
Yeah, I'm present, sir.
Pradeep G. Bhatt has received his BSc and MSc degree from Karnataka University, Dharwad, India, in
In a short
1984 and 1986
Let the
respectively.
organizers
He
start
then
the program.
pursued his PhD from Bangalore University, Bangalore, in the year 1998.
Yes.
He
Good
is
afternoon to
currently
all.
working as professor
Myself,
in
Rakesh, Head
Manipal
of the
Institute
Department
of
of Mathematics,
Technology,
Poornaprajna College,
Manipal
Udupi.
Academy of Higher Education.
First of all, I
Manipal,
welcome all of
India.
you to this paper presentation session.
At
So here we have with us Dr.
coordinator
Raghavendra
in
A,
Department of
Associate
Science,
Professor in
MIT,
Mathematics,
Manipal.
Poornaprajna College, to chair the session.
He serves
So it's
as
my immense
head of
pleasure to
he has served
introduce
as
Raghavendra sir. He obtained his
2013
MSc and MPhil degree from Mangalore
in
University.
MIT, Manipal.
He was awarded
He serves as
a doctoral
referee
degree,
to
PhD,
several
by
reputed
Dravidian University
international journals.
for a thesis on
He has
distinct
several
sets of graphs
publications in
and groups.
reputed
He has
Scopus and
presented
Web of Science
papers
journals.
in several
He is
national
currently guiding 3 research scholars and guided 6 research scholars previously. Welcome you, sir. Over to you, sir.
Start the session, sir.
Hello. Prasanna, can you hear me?
Yes, sir. We are able to hear you.
Yeah. Thanks for the presentation by Gautam Shanay about me. Okay. So we can start.
First presenter.
Hello.
Gautam Virappu. BG presentation topic: BG polynomial of graphs.
Department of Mathematics, Karnataka University, Dharwad. Title of the paper is BG polynomial of a graph. And this is abstract of the paper. In this paper, we introduce the BG polynomial of a graph. In addition, we propose the chromatic harmonic index and chromatic inverse sum index, and we obtain BG polynomial of cycle-related graphs. Also, we obtain the second chromatic diagram index, chromatic inverse sum index, and chromatic harmonic index of cycle-related graphs. Furthermore, findings are interpreted graphically. So before going to understand the BG polynomial of a graph, we should understand terminologies. Here the graph indices. Graph indices are also called as the topological indices. Topological indices are the numerical parameter which are associated with the molecular graph of a chemical compound, which plays important role in determining physical and chemical properties of chemical graphs. Here the two indices, harmonic index of graph G and inverse sum index of graph G. Graph coloring. Suppose C with a set of color C1, C2 up to Cl with the number of colors in set C. If you color the vertices of G in such a way that first color is assigned to maximum possible number of vertices, the second color is assigned to maximum possible number of remaining uncolored vertices, and proceed in this manner until all vertices are colored, then such a coloring is called simultaneous coloring of graph G. In a similar manner, Cl is assigned to maximum possible number of vertices, then Cl is assigned to maximum possible number of remaining uncolored vertices, and proceed in this manner until all vertices are colored, then such a coloring is called Cypress coloring of graph G. Here the chromatic J graph indices has been proposed by Johann Koch et al. This is the definitions of the chromatic J graph indices. The first chromatic J graph index, the second chromatic J graph index, and third chromatic J graph index, and the chromatic total irregularity index of graph G. And the M polynomial was introduced by Dutch and Kaufzer in 2015. These are our contributions. So motivated by previous research on chromatic topological indices, we now propose the chromatic harmonic index, the chromatic inverse sum index of graph G. The definition of the chromatic harmonic index of G denoted by Ch to the power psi t of graph G, and is defined as sum of I equal to 1 to n minus 1, sum of j equal to 1 to n, 2 divided by zeta vi plus zeta vj. Here vi and vj belongs to edge set of graph G. A chromatic inverse sum index of graph G denoted by Ci to the power psi t of graph G, and is defined as the sum of I equal to 1 to n minus 1, sum of j equal to 1 to n. It is the product of zeta vi plus zeta vj whole divided by zeta vi plus zeta vj. Vi and vj belongs to edge set of G. And motivated by previous research on M polynomial in the name of my research guide Professor B. Basona Gaud, we now introduce the BG polynomial of a graph. Let G be a graph and G with a set of colors be a proper coloring of G. Then the BG polynomial of a G is defined as neta of Ts, x to the power Ct and y to the power Cs, where neta of Ts is the total number of edges with n points having color Ct and Cs. Here Ct and Cs belongs to color set C. This table gives operator to derive chromatic harmonic index and chromatic inverse sum index from the BG polynomial. Similarly, this table gives operator to derive second chromatic J graph index from the BG polynomial. Already we are familiar with the wheel graph. If you are attaching the pendant edges to the rim of that wheel graph, we get a Helm graph. So a flower graph Fn is a graph which is obtained by joining the pendant vertices of Helm graph to its central vertex. We get a flower graph denoted by Fn. And it has a vertex set 2n plus 1 and edge set 4n. Here the simultaneous coloring of flower graph for even values and odd values. For even values, the flower graph has chromatic number is 3 and chromatic number 4 for odd values. Here the BG polynomial of flower graph for simultaneous coloring of graph G. G is our flower graph. And by using this BG polynomial, we obtain these results: chromatic harmonic index, chromatic inverse sum index, second chromatic J graph index for simultaneous coloring of G. So BG polynomial for psi plus coloring of flower graph Fn. These are the obtained results. And this graphical comparison shows the maximum and minimum values of second chromatic J graph index for flower graph Fn, the chromatic harmonic index. This is chromatic inverse sum index. A sunflower graph. A sunflower graph SFN is a graph obtained by replacing each edge of the rim of the wheel graph by a triangle such that two triangles share a common vertex if and only if the corresponding edges in wheel graph are adjacent in wheel graph. Sunflower graph has vertex at 2n plus 1 and edge at 4n. Here the Simon-Welles coloring of sunflower graph for even values and odd values, and chromatic number is 3 for even values and chromatic number 4 for odd values. So BG polynomial of sunflower graph, and these are the obtained results. So BG polynomial of sunflower graph, it is for psi plus coloring of sunflower graph, and these are the obtained results. These are the graphical comparison between a maximum and minimum values of second chromatic J graph index for psi plus coloring and Simon-Welles coloring. And this plot for this graphical comparison between maximum and minimum values of chromatic harmonic index of sunflower graph, and this is for chromatic inverse sum. And this is for the next graph is closed sunflower graph. A closed sunflower graph is a graph obtained by joining the independent vertices of sunflower graph which are not adjacent to its central vertex, so that these vertices induce a cycle on n vertices. This is BG polynomial of closed sunflower graph. These are the obtained results. BG polynomial of closed sunflower graph for psi plus coloring. These are the obtained results. These are the graphical comparison which shows the maximum and minimum values of second chromatic J graph index of psi plus coloring and psi minus coloring of closed sunflower graph. Chromatic harmonic index, and this is for chromatic inverse sum mix of closed sunflower graph. Similarly, one can get the BG polynomial and chromatic topological indices for remaining graphs, and last graph is blossom graph. By the blossom graph is the graph obtained by joining all vertices of the outer cycle of a closed sunflower graph to its entire vertex. It has vertex at 1 plus 1 and edge at 5n. In both the cases, the chromatic number is 5 for odd values and even values. BG polynomial of blossom graph. These are the obtained results. BG polynomial of psi plus coloring of graph. These are the obtained graphical comparison between maximum and minimum values of second chromatic J graph index of psi plus coloring and psi minus coloring of blossom graph. This is for chromatic harmonic index. This is for chromatic inverse sum index. This work is supported by Karnataka University Dharwad through University Research Studentship. These are the references. The reference number 4, 5, 6 and 7, which I have gone through for chromatic topological indices. So thank you one and all.
Any question from the participants? Gautam Shanai. Hello.
Yes, sir. Yes, sir.
Why did you select the such graph sunflower and blossom graphs close to blossom to get the BG polynomial?
Sir, actually it is, sir, am I audible, sir?
Yes.
Sir, it has some edge-based, hello?
Yeah, I can hear you. Yeah, tell me.
Okay, sir. In general, it cannot be possible, sir. Some class of graphs, it is possible, sir. To finding the chromatic number for some class of graphs, it is possible, sir.
Correct. So why did you select sunflower and the three classes? What are the motivation behind that?
And it is a wheel related and also it is cycle related graph, sir. If any graph, the cycle and wheel is common to all those.
Yeah, and you are getting cubes also, Cube,
yes, sir.
I think
yes.
you did not try. Yeah, did you try that?
No, sir. I'm just trying for in general for a generalized derived and graphs.
Okay. And you have showed the maximum and minimum of in a graph,
Yes, sir. Yes, sir.
What is the correlation behind that?
Sir, actually, the minimum parameter coloring. Suppose I will take the one triangle, sir. So triangle means 1, 2, 3. We can label it as 1, 2, 3.
Okay.
We get a 3 factorial. The chromatic number of triangle is 3, sir.
Yeah.
So we get a 6 different graphs with a different labeling, sir.
Okay.
So out of 6 graphs, the one graph shows the maximum value and other graph shows the minimum value, and whatever the remaining graphs is no sir. Suppose 4 graphs, 6 graphs out of out of 6 graphs, 2 graphs already we found that maximum and minimum value. Out of that, the remaining 4 graphs, the value lies between those 2 graphs.
Briefly
That is
explain
numeric
the
value.
abstract of this paper.
Okay.
Numeric values lies between
And
those two.
H A, D anti-magic labeling in H decomposable graph. G is a bisection. F from V of G union E of G to 1 to etc. up to P plus Q, such that summation F of Hi, where I varies from 1 to H, forms an arithmetic progression with difference G and the first element A. We say that F is HV super A, D anti-magic if this F of V, G receives the smallest label, and if V of G can be partitioned into U of G and V W of G with the cardinality M and N, then this F is said to be HV super strong A, D anti-magic labeling. And this HV super strong A, D anti-magic labeling, we call it if this first set F of U of G receives the smallest one, 1 to up to M, and the F of W of G receives M plus 1 to M plus N, where which is nothing but P. A graph that admits HV super strong A, D anti-magic labeling is called a HV super strong A, D anti-magic decomposable graph. In this paper, we prove that the complete bipolar graph K, M, N are HV super strong A, D anti-magic decomposable with both M and N are even. Let me briefly explain about the introduction of this paper. So Horsfield and Ringel introduced the concept of anti-magic graph. And in the terminology, an anti-magic labeling is an edge labeling of the graph with the integers 1 to etc. up to q, so that the weight on each vertex is different from weight at any other vertex. And Bodendijk and Walther define the concept of an A, D arithmetic anti-magic labeling as an edge labeling in which the vertex weights forms an arithmetic progression starting from A and having a common difference T. Baca et al. Introduced the notions of vertex anti-magic total labeling and A, D vertex anti-magic total labeling. Simon Jutek et al. Introduced the concept of A, D anti-magic graph. And Sudarsana et al. Introduced studied the concept of super edge anti-magic total labeling of disconnected graphs. The main definition. So, as in the abstract, so a bisection F from U of V of G union E of G to the integers 1 to etc. P plus Q is called a vertex anti-magic total labeling. If the weights of the vertex forms are pairwise distinct. F is called an A, D vertex anti-magic total labeling of G if the set of vertex weights forms an arithmetic progression for some integer A and T. F is said to be super A, D vertex anti-magic labeling if the vertices receives the smallest labeling. So that is F of V of G is equal to 1 to etc. up to P. Graph G is called super A, D vertex anti-magic if it admits a super A, D vertex anti-magic labeling. Similarly, a bisection from V of G union E of G to the vertex to the integers 1 to etc. up to P plus Q is called an A comma D edge and magic total labeling of G. If the edge weights forms an arithmetic progression with the first term A and common reference T. And such F is said to be super A comma D edge magic labeling if F of V of G is equal to 1 to etc. up to P. A graph admitting such a labeling is called super A comma D edge and magic labeling. And the covering of G is a family of subgraphs. Such one is to etc. height such that each edge E of G belongs to at least one of the subgraphs such then it is said to be that G admits an one is to etc. H covering. If every HI is isomorphic to a given subgraph H, then we say that G admits the H covering. Similarly, a family of subgraphs H1, H2, etc. H of G is an H decomposable of G if all the subgraphs are isomorphic to a graph H. And in this case, this edge E of Hi and intersection E of H is equal to empty for I not equal to J. And if you take the union of all the edges, it is nothing but the edge set of the original graph. In this case, we write G is equal to the decomposable can be written as H1 addition modulo, H2 addition modulo, etc. addition modulo HH. The notion of H super magic labeling was first introduced and studied by this Gutierrez and Lado in 2005. So they proved that some classes of connected graphs are H super magic. So we introduced the concept of this HV super magic labeling and HE super magic labeling as in the previous cases. So a total labeling F from V of G union E of G to 1 theta P plus Q is called H magic labeling of G if there exists a positive integer K such that for every copy H in the decomposition, the sum of F of H is equal to sum of the vertex set F of V and the sum of the edge set is equal to K. A graph that admits such a labeling is called H magic decomposable graph. So we introduced the concept of this HV super magic labeling and HE super magic labeling. So H magic labeling F is called HV super magic labeling if the vertices receives the smallest label, and if it is said to be the HE super magic labeling if edge set receives the smallest label, and the sum of all vertex and edge labels of H is denoted by summation F of H. In 2001, McLaren's battle introduced the concept of super strong magic labeling of bipartite graph as in the name of super, a special super magic labeling in bipartite graph, and it was renamed as super strong magic labeling by Moore and Wallace. Myself and my guide, we introduced the concept of HV super strong magic decomposable and HE super strong magic decomposable of complete bipartite graphs. By studying that paper, so we found that something is missing for the cases of M and N are even, and M and N are not even. So the concept of HV super strong magic decomposable graph and HE super strong decomposable graph was introduced by us. So it is nothing but G is a bipartite graph with vertex sets V1 and V2 of sizes M and N respectively, and edge total labeling of G is a super strong if the edges of V1 receives labels 1 to etc. up to M, and the elements of V2 receives the labels M plus 1 to M plus N. So with this idea, we had introduced the concept of HV super magic decomposable graph. So graph H is H decomposable if the vertex set is divided into union of two partition with the U of G cardinality is equal to M and W of G is equal to N. Modulus of W of G is equal to N. And HV super magic labeling F is called HV super strong magic if F of U of G is equal to 1 to etc. M and F of W of G is equal to M plus 1 to M plus N. A graph admits such a labeling is called HV super strong magic decomposable graph. Similarly, if the vertices receives the instead of the vertices receives the smallest one, it's HE super magic labeling can be defined if F of U of G, so that is the vertex set receives the remaining Q to Q plus M plus N. So that is Q plus 1 to Q plus M, and F of W of G is equal to Q plus M plus 1 to Q plus M plus N. So a graph that admits such a labeling is called a HE super strong magic decomposable graph. So with this idea, so we had introduced this concept of H V super A, T super strong antimagic graph. So getting into the main results, in this section we consider the graphs G is always isomorphic to K M, N, and the subgraph H is isomorphic to K1, N, where N is greater than or equal to 1. And we assume that both M and N are even. And in this case, we have P is equal to M plus N and Q is equal to Mn. The first result, it states that suppose if H1, H2, etc., Hm is an n-star decomposable graph, decomposition of G with both M and N are even, then this G is HV super strong A, D antimagic decomposable with the first element A is equal to 1 plus N square into M plus 3 plus 2N into 2M plus 1 divided by 2, and the difference, common difference, D is equal to 1. And we had given the second result, it states that if a non-trivial H decomposable graph is HV super strong E, D antimagic decomposable graph with both M and N are even, and if the sum of the edge labels of a decomposition Hj is denoted by summation f of E of Hj, then this summation f of E of Hj is constant for all j varies from 1 to m, and it is given by this number n square into m plus 2 plus n into 2m plus 1 divided by 2. Similarly, if a non-trivial H decomposable graph with HV super strong A, T antimagic decomposable with both M and N are even, and if the sum of the vertex labels of the decomposition Hj is denoted by summation f of V of Hj, then this summation V of Hi, this forms this set, it forms an arithmetic progression with first element A and the difference D. So it forms A to A plus D, etc., A plus M minus 1 D, where this A is given by Mn plus 1 plus N into N plus 1 by 2 with D is equal to 1. And our last result, it states that suppose if G is a H decomposable graph with both M and N are even, and if V of G is partition into U of G and W of G with the modulus of number of elements in U of G is equal to M and number of elements in W is equal to N. Let G be a bijection from V of G onto 1 except up to P with G of U of G is equal to 1 to M and G of W of G is equal to M plus 1 to M plus N. Then this D can be extended to an HV super strong A, T antimagic labeling if only if this summation F of Hj is constant for all j varies from 1 to M, and that number is given by summation F of E of Hj is equal to N square into M plus 2 plus N into 2M plus 1 by 2. So in this paper, we had studied about this HV super strong A, T antimagic decomposable on of K, M, N with the N greater than or equal to 1. And in the here, this K, M, N is HV super strong A, T magic only in the case that M and N are even. For all the other cases, it satisfies the HV super strong magic decomposable. So for when M and N are odd, and M is odd and N is even, and N is odd and M is even, for all the other three cases, this K, M, N satisfies HV super strong magic decomposition, which was already done in our previous paper, and it was communicated. And these are the references that we had used, that I had used for this paper. So reference number 14 and 15, it was communicated. So it states about the T super magic decomposition of complete white bubble graphs, and 15 also HV super strong magic decomposition of complete white bubble graphs, which was communicated.
Any questions, anyone?
Thank you.
Okay, now congratulations, good work. But
thank you.
Your work I really appreciate. But thing is, the presentation here, when it is a paper presentation, mainly when you are restricted to 8 to 10 minutes, it's better if you highlight the important work. That is, you have defined something new here. Okay.
Yes, sir.
Give more emphasis on such things and with examples. You have not given any example here.
Yes, sir. Yes.
Okay? Because when it is a new concept, anyone would like to understand it at the preliminary level, basic level.
Okay.
So for presentation part, you need to take care. Content is good.
Okay, sir. Okay. Thank you, sir. Thank you, sir.
Shruti?
Yes, sir. Present, sir.
Yeah. Now your session.
Yes, sir.
Let the organizers play the video.
Yes.
Hello, everyone.
As I can see, the topic is on k-difference secure graphs.
Hello everyone, I'm Sunita Priya De Silva, SSM professor at Sahyadri College of Engineering and Management. I have done my research under the guidance of eminent professor Dr. B. Sura Narayana at Dr. Ambedkar Institute of Technology, Bangalore. Today's topic of my presentation is on k-difference secure set. These are the overviews of my presentation: abstract, introduction, main results, and references. In this paper, we consider only finite simple connected graphs. Let G, V, E be any graph. Let F be a mapping from V to 1, 2, 3 up to cardinality of V be a bijection. A graph G, V, E is called an arbitrary k-difference secure if every k element subset of V is a difference secure set. The maximum k such that G is k-difference secure set is called k-difference secure number of G, and it is denoted by dsn star of G. Here we find some bounds and study about certain structural properties of the k-difference secure sets of the known graphs. Introduction. In one array, I have introduced the concept of difference secure graphs. A graph is called difference graph if there is a bijection F from the set V to the set of positive integer n such that any edge xy is an edge if and only if the cardinality of modulus of f of x minus f of y belong to n. Further, the study on these graphs are carried on these papers, which are referred in 3, 4, 5, 6. If the codomain of F is restricted to cardinality of V, we can define difference secure set. Given the cardinality of V labels the maximal set S of vertices in a graph G such that the induced graph S is a difference secure graph is called difference secure set. A difference secure set is called a maximal difference set if it is not a proper subset of any other difference secure set of G. Among all such F, the minimum cardinality of a maximum difference secure set is called the lower difference secure number of G, and it is denoted by DSN of G. Likewise, the maximum cardinality of maximal difference secure set is called the upper difference secure number of G, and it is denoted by DSN of G, capital DSN of G. We understand with an example of a difference secure number. Consider a graph G with vertices A, B, C, D, E, F. Now, if we take the set A, C, B, and D, a subgraph S, and if we label them as 1, 2, 3, and 6, and remaining 2 by 4 and 5, this set which we are given S satisfies difference secure property. We cannot include 4 in this set, the vertex 4, as there creates an edge between E, vertex V, and vertex E. Similarly, 5 cannot be included here because there creates an edge between A and D. Hence, we say that the maximal difference secure set is A, B, C, D with the labels 1, 3, 2, 6. Now we consider this subgraph with the set D, E, F and label them with so we can see it satisfies the difference graph because 4 minus 3 is 1. We have an edge over here. Difference in 1 and 3 it is 2. It is not present over here. And 4 minus 1 is 3. It is present over here. And if we label this by other remaining numbers, we observe that none of these numbers can be included in this set S. So we say that this set containing D, E, F is a maximal set with the f of s is equal to 4, 1, 3. Hence we observe that the first set A, B, C, D is the maximal set with the maximum cardinality, and the set D, E, F is the maximal set with the minimum cardinality. Hence we can say that capital DSN of G is equal to 4 and small DSN of G is equal to 3. Next definition, a graph is called an arbitrary k difference secure set if for every k element subset of V is a difference secure set. The maximum k such that G is k difference secure set is called k difference secure number of G, and it is denoted by DSN star of G. It is obvious that DSN star of G is less than or equal to DSN of G. Now we understand this with an example of k difference secure number. Consider a graph G. Here we have given all the possible sets with cardinality 3. If we observe S1, S2, S3, S4, if you consider these set and we label these set with 1, 2, 4, it satisfies the difference secure property. Similarly, the set S5, S6, S7, S8 and S9 satisfies difference secure property with the label 1, 2, 5, and this set S10 with A, C, E with cardinality with labels 1, 3, 5 satisfies difference secure property. But if you consider a set with cardinality 4, that is, if you consider set A, B, C and E, and with the given elements, with the given labels 1, 2, 3, 4, 5, it is not possible to label this subgraph such that it satisfies the difference secure property. Hence, the set of having cardinality 4, there exists at least one set with cardinality 4 which does not satisfy the difference secure property. So we say that the maximum K which satisfies the difference secure property is 3. So dsn star of G is equal to 3. Main results. Observation for any graph G is equal to V, E, we have the graph G of order n greater than or equal to 3 then dsn star of G lies from 2 to n. The complete graph G is always n difference secure set. Proposition for any graph G with order n greater than 3, if G is isomorphic to Kn or G is isomorphic to Kn minus E, then dsn star of G is equal to dsn of G. But the converse of the above theorem is not true because there exists a graph with dsn star of G is equal to dsn of G, but it is not equivalent, not isomorphic to Kn or Kn minus E. Theorem: let G be a graph of order n containing a pendant vertex V if G minus V is equal to Kn minus 1, then dsn star of G is equal to ceiling n by 2. Lemma: if G is a graph of order n greater than or equal to 6 as an induced subgraph K2, 4 complete bipartite graph, then dsn star of G is less than or equal to 5. An independent set is a set of vertices in a graph where no two of which are adjacent. The independent number of G is denoted by alpha of G and the maximum size of the independent set is in G. Let G be any graph of order n. Let F be a mapping from V of G to positive n numbers, be a bijection. If the set S is a difference secure set and it is independent, then the cardinality of S is less than or equal to ceiling n by 2. The dsn star of K1, n, that is a star graph, is equal to ceiling n plus 1 by 2. For a complete bipartite graph Kp, Q with P less than or equal to Q, dsn star Kp, Q is equal to ceiling Q by 2 when P is equal to 1, P plus 1 minus 1 for P2 and Q lying from 1 to 3, 4 when P and Q is equal to 3 and 5 otherwise. For any path Pn, dsn star of Pn is greater than 2k when k is equal to ln to the base 2 n plus 1 by 3 minus 1. A definition: a UV path is a monophonic path for any two vertices u and v in a connected graph G if it contains no chords and the monophonic distance dm u, v is the length of the longest u minus v u v monophonic path in G. Corollary: for any independent graph G, if there exists a UV monophonic path with distance dmu comma v is equal to L, then dsn star of g is greater than 2k when k is equal to ln to the base 2 L plus 1 by 3 minus 1. For any n greater than or equal to 3, a wheel graph w1 comma n dsn star w1 comma n greater than 2k where k is equal to ln to the base 2 n by 2 minus 1. Lemma. For any graph G with k different secure set with respect to a bijection function f, if G has a subgraph H as shown in this figure, then k is less than 5. A generalized wheel denoted by Wm, n is a graph obtained by joining the vertices of Km complement to every vertex of a cycle Cn, that is Wm, n is equal to Km complement plus Cn. The m vertices of Km complement and n vertices of Cn in Wm, n are respectively called the central vertices and the rim vertices of Wm, n. For any m greater than 1 and n greater than or equal to 3, the graph for the graph Wm, n, dsn star of Wm, n is equal to 4. And these are the references. Thank you. A heartfelt gratitude to the management and the staff of Poornaprajna College for organizing this conference and giving me an opportunity for presenting this paper. Thank you, one and all.
Thank you for the presentation, ma'am. It was indeed wonderful. Any questions from the audience?
We have considered octane isomers. So we have got the correlation with the octane isomers.
Any other such indices being used you are aware of?
Sir, there are many indices, Jagrab indices, hyper Jagrab indices. There are many, sir.
Okay, good.
Okay.
Thank you.
Sir. Thank you, sir.
Mr. Mohammed Sadek?
Yes, sir. Good morning to all. Myself, Mohammed Sadiq Sayed, research scholar, Department of Mathematics, Karnataka University, Dharwad. Under the guidance of Dr. B. Basavanagoda, Department of Mathematics, Karnataka University, Dharwad. Today I am presenting a paper on certain topological indices of Basava windmill graph. In this paper, we have proposed a windmill graph that is a Basava wheel windmill graph. The Basava wheel windmill graph W1 plus 1 M is a graph obtained by taking M copies of the graph, that is K1 plus Wn, for n should be greater than or equal to 4 with a vertex K1 in common. We have obtained first and second Jagrab index, F index, first and second hyper Jagrab index, harmonic index, randic index, general randic index, sum connectivity index, general sum connectivity index, atom bond connectivity index, geometric arithmetic index, symmetric division degree index, and so more indices of Basava wheel windmill graph. Inspired by recent work on topological indices, proposed degree-based topological indices, that is general SK alpha and SK1 alpha indices of graph G. We also obtained general SK alpha and general SK1 alpha indices of Basava wheel windmill graph. In the field of chemical graph theory, a topological index is known as a connectivity index. It is a type of molecular descriptor that is calculated based on the molecular graph of a chemical compound. Topological indices are numerical parameters of a graph which characterize its topology and are usually graph invariant. Topological indices are used, for example, in the development of quantitative structure activity relationship, in which the biological activity or other properties of molecules are correlated with their chemical structure. Topological descriptors are derived from hydrogen suppressed molecular graphs, in which the atoms are represented by vertices and the bonds by edges. In this paper, we have considered only finite undirected graph without loops and multiple edges on n vertices and m edges. That is called NM graph. Vertex set as denoted as V of G and edge set as denoted as E of G. The degree of a vertex V is the number of edges incident to V is denoted by degree of G of V. In the literature, wheel graph is already defined. Wheel graph is nothing but a graph obtained from a cycle graph Cn-1 by adding a new vertex. That is nothing but Wn equal to K1 plus Cn-1 is a graph with n vertices and 2n edges. Nowadays, topological indices are extensively used in mathematical chemistry. In the literature, many researchers are defined degree-based topological indices. In that, some indices are well known, that is first and second diagram indices, forgotten topological index or F index, first and second hyperdiagram indices, harmonic index, Randic index, sum connectivity indices, general Randic index, general sum connectivity index, atom bond connectivity index, geometric arithmetic index, symmetric division degree index, Sombor index. This is the Basova wheel wheel graph. Here we have taken m copies of the wheel graph. Every vertex of wheel graph is adjacent to a common vertex, that is K1. So wheel graph, Basova wheel wheel graph is nothing but a K1 plus W1. Means the common vertex is adjacent to every vertex of the wheel graph. This Basova wheel wheel graph is having a mn plus 1 vertices and 3 mn minus 2m edges. Here we are given one proof of the F index of Basova wheel wheel graph is nothing but F of W1 plus 1 m is equal to 64m into n minus 1 plus mn cube into 1 plus m square. Here we have used the algebraic method. In Basova wheel wheel graph is having a 3 partition of vertex sets and 4 partitions of edge sets. That is the degree 4 is having a m into n minus 1 vertices, degree n is having a m vertices, and degree mn is having a only one vertex. Similarly, it's having a 4 partitions of the edge set. That is the degree of u of degree of g of u and degree of g of v is 4. Then it's having a m into n minus 1 edges. Degree of g of u is 4 and degree of g of v is n. Then it's having a m into n minus 1 edges. Degree of g of u is 4 and degree of g of v is mn. It's having a m into n minus 1 edges. Degree of g of u is n and degree of g of v is mn. Then it's having a m edges. After simplification, we get the desired result 64 m into n minus 1 plus m into n cube into 1 plus m square. This is the obtained result of harmonic index of Basova wheel wheel graph. And this is the desired result of Randic index of Basova wheel wheel graph. And this is the general Randic index of Basova wheel wheel graph. This is the second diagram index of Basova wheel wheel graph. And this is the second hyperdiagram index of Basova wheel wheel graph. Second diagram index and second hyperdiagram indices are the corollary of general Randic index. This is the desired result of general sum connectivity index of Basova wheel wheel graph. And this is the general sum connectivity index of Basova wheel wheel graph. And this is the first diagram index of Basova wheel wheel graph. And this is the first hyperdiagram index of Basova wheel wheel graph. These are the corollary of the general sum connectivity index. And this is the desired result of atom bond connectivity index of Basova wheel wheel graph. And this is the obtained result of geometric arithmetic index of Basova wheel wheel graph. And this is the symmetric division degree index of Basova wheel wheel graph. And this is the Sombor index of Basova wheel wheel graph. In the literature, Sigedi and Conbour is already defined SK indices, that is nothing but a summation of UV block create set of G, degree of G of U plus degree of G of V divided by 2. Further, we have extended to its a general form, that is the general SK alpha and general SK1 alpha indices of graph G. The general SK alpha index of a graph G is defined as SK alpha of G equal to summation of UV block create set of G, degree of G of U plus degree of G of V divided by 2 whole raised to alpha. If I put alpha equal to 1, then we get the SK index. If I put alpha equal to 2, then we get the SK2 index of a graph G. That is SK2 of G equal to summation of UV belongs to set of G, degree of G of Q plus degree of G of V divided by 2 whole square. Next, further we have extended general SK1 alpha of G. That is in the literature, Sigid and Kanpur is already defined. It's a product form. In previous, it's a sum form is there. In that, it's a product form. That is a SK1 of G equal to summation of UV belongs to set of G, degree of G of U into degree of G of V divided by 2. Again, we have extended it's a general form. That is a SK1 alpha of G equal to summation of UV belongs to set of G, degree of G of U into degree of G of V divided by 2 whole raised to alpha. If I put alpha equal to 1, then we get a SK1. That is a divided by SK1 1 of G. If I put alpha equal to 2, then we get the desired equation, that is SK1 square of G equal to summation of U belongs to set of G, degree of G of U into degree of G of V divided by 2 whole square. And this is general form of SK alpha, index of Basova-Weil-Windmill graph. Means obtained results. This is. And yes, this is the desired result of SK1 index of Basova-Weil-Windmill graph. And this is the SK2 index of Basova-Weil-Windmill graph. These are the corollary of general SK alpha index of Basova-Weil-Windmill graph. And this is a general SK1 alpha index of Basova-Weil-Windmill graph. This is a desired result. And this is the obtained result of SK11 index of Basova-Weil-Windmill graph. And this is the desired result of SK1 square index of Basova-Weil-Windmill graph. These are also corollary of the general SK1 alpha index of graph G. Chemical graph theory is an essential tool for studying molecular structure and has an important impact on the development of chemical sciences. The study of topological indices is one of the most active studied field in chemical graph theory. We have presented here few theoretical results on the some degree-based topological indices. We have proposed a new graph transformation, that is Basova-Weil-Windmill graph. And also we have proposed two topological indices, namely general SK alpha and general SK1 alpha indices. Using these indices, we can obtain physiochemical properties of molecular graphs. This work is partially supported by Directorate of Minorities, Government of Karnataka, Bangalore. And these are I have referred the references. In that, Sigid and Kanpur indices define the degree-based topological indices graphing. Thank you.
Okay, good one. Congratulations. Any questions? Yeah, your presentation also was good. Preparation, PPT, everything was good. The new work, okay, good attempt. Yeah, I have to congratulate for attempting to bring out new work.
Thank you, sir.
Yeah. Okay. Yeah. Thank you, Mr. Sadiq. Mr. Jyotiraj. He has not turned, I think. Jyotiraj there? No. The last one in the list, Mr. Harsha. Is it Harsha AJ?
Yes, sir, I'm there.
Yeah.
This is Harsha AJ from the Department of Mathematics at St. Joseph Engineering College, Mangalore, Karnataka. Today I'm going to present my paper work based on graph of a lattice and its properties. At the outline, I would like to present introduction of the work, then notations and definitions which are required for this particular presentation. Then straight away I will move on to graph of a lattice with respect to an ideal, and that be denoted by Gi of L. And at the end, we have conclusion and future work followed by a reference. Basically, the motivation behind this particular work is the paper by Satyanarayana Bhonari and others. The paper title is Graph of a Near Ring with respect to an ideal. It was published in 2010. So in this particular paper, the authors studied graph of a near ring with respect to an ideal, and they denote that particular graph as Gi of n. In the same paper, they have defined a new type of symmetry of Gi of n. And they proved that ideal symmetry of Gi of n implies by the symmetry determined by the automorphism group of Gi of n. So all this work is based on earrings. What we thought is it possible to work the same way in terms of a lattice structure? So we started working on that. What we have done is we introduced a concept called graph of a lattice L with respect to an ideal I, and that we denoted by Gi of L, and we proved that prime graph of a lattice L is a subgraph of L with respect to any ideal of L. And these are the basic definitions which are required. Throughout this presentation, G contains a set of vertices E of G and set of edges E of G. And an edge between two vertices x comma y belongs to V of G is denoted by xy bar. And if S is a subset of V of G, we denote G minus S, the graph whose vertex set is V of G minus S and whose edge set is E of G minus S. And a vertex cut of G is a subset S of V of G such that G minus S should be disconnected. In same way, we can define edge cut. Edge cut of G is a subset T such that the graph G minus T should be disconnected. To continue with that definition, we have taken two more terms. One is vertex connectivity and edge connectivity. Vertex connectivity is denoted by K of G, that is minimum number of edges vertices to be removed so that graph should be disconnected. Otherwise, we take it as infinity. Similarly, we can define edge connectivity and it is denoted by lambda of G. That means minimum number of edges to be removed so that graph should be disconnected. Otherwise, we take it as infinity. And last one is delta of G, that represents minimum of degree of V, where V is the vertex set of V. And in general, vertex connectivity is always less than or equal to edge connectivity, which is less than or equal to delta of G. Now, this is the second concept we have covered in this particular presentation, that's lattice theory. Basically, lattice is a partially ordered set or poset in which if you take any two elements which has a supremum and infimum, or we call it as meet and join. A lattice which contains both minimum and maximum element is called a bounded lattice. Therefore, throughout this presentation, L denotes a finite lattice with minimum element 0 and maximum element 1. An element A of a lattice L is called an atom of L if L has the minimum element 0 and 0 should be covered by A. And when we say a lattice is said to be atomistic, if every non-zero element of L is join of atoms contained in it. And the last and important definition is, what is the meaning of ideal of a lattice? So ideal I of a lattice L, it should be a non-empty subset and it has to satisfy these two conditions. The first condition is A comma B belongs to I implies its join, that is A join B should be belongs to I, and also A belongs to I and X belongs to L implies A meet X should be in I. Then we call the set I as ideal of a lattice L. In continuation with that definition, an ideal I of a lattice is called a prime ideal. It has to satisfy one more additional condition. The additional condition is if xy belongs to L, x mate y belongs to I implies either x belongs to I or y belongs to I. A prime ideal I of a lattice L is said to be a minimal prime ideal if there is no prime ideal which is properly contained in I. So these are the preliminary definitions required. Now we will move on to our work. The first term what we defined is graph of a lattice with respect to an ideal. So how we have defined this? Let me consider I, it is an ideal of L. Then the graph of L with respect to an I is a graph. So first of all, it should be a graph with each element of L as a vertex. That means what are the elements are there in S? Suppose we have artist L contains 5 elements. That 5 elements will be considered as vertices of a graph G. And two distinct vertices X and Y are connected by an edge if and only if its meet, that is X meet Y should be belongs to I. And we denote this graph as Gi of L. And in particular, the prime graph of a lattice L means it is a graph with respect to ideal I equal to 0. For the better understanding, Let's see with an example. This is a simple example. I have taken a simple lattice with 4 elements. Minimum element is 0, maximum element is 1, and we have 2 more elements A and B. Now we have 4 ideals. First one is 0, I2 is 0 comma B, I3 is 0 comma A, and last one is the entire lattice itself is an ideal. Now look at this figure 2. This is the graph of a lattice corresponding to the ideal I1. I1 means 0. So how to construct the graph? It is very simple. Here we have 4 elements. The same thing you have considered as a vertex. There is no order, anyway you can put up. So 0, A, B, 1 are the vertices. Now I can connect edge between any two vertices if and only if its meet should be in I. So in this case we have only 0 in the ideal, right? Therefore I have connected A and B because in the lattice L A meet be 0 and 0 belongs to I. So that's why there is a connection between A and B. Similarly I have connected A0, B0 and 0 1 because meet of all these elements come up with 0 and that belongs to I. But I have not connected B and 1 because if you find the meet of B and 1 in a lattice L, B meet 1 is B, but that is not there in ideal. So that's why there is no connection between B and 1. So this is the graph we obtained corresponding to the ideal I equal to 0. Similarly, this is the graph corresponding to the ideal I2. This is the graph corresponding to the ideal I3, and this is for I4. The principle remains same. When we see all these structures, it's very clear that GI of L is connected graph without self loops and multiple edges. The maximum distance between any two vertices of GI of L is at most 2. Now, based on this observation, if I and J be ideals of L such that I is contained in J, then G0 of L, that means ideal corresponding to 0, is contained in GI of L, which is contained in Gj of L, and that is contained in GL of L. Now, we will define 2 more terms. One is strong vertex cut and strong vertex connectivity. So, strong vertex connectivity means that is denoted by capital K of G, minimum number of vertices to be removed so that graph should be totally disconnected. So, that we call it as strong vertex connectivity, that is denoted by capital K of G. Based on this definition, we prove that let I be an ideal of L, I is a prime if and only if I is a strong vertex cut of Gi of L. So this is the outline of the proof. So I'm not going to explain this. Based on this, we have a corollary which says let I be a minimal prime ideal of L, then Kgi of L, that is strong vertex connectivity, is always equal to number of elements in I. And let I be a prime ideal of L, lattice L, then X belongs to I if and only if degree of X should be equal to degree of 0 in Gi of L. So this is the outline of the proof. The next proposition, let I be an ideal of L with the number of elements in L is n and number of elements in I is n. Of course, n should be m should be less than or equal to n. So if I is a proper ideal of L, then Kg of L, lambda G of L, and delta G of L, that is vertex connectivity, edge connectivity, and minimum degree is always equal to number of elements in I. If I equal to L, then that is equal to n minus 1. So this is the outline of the proof. The next definition, the graph Gi of L is said to be ideal symmetric if for every xy bar in Gi of L, either degree of x equal to degree of 0 or degree of y should be equal to degree of 0. Based on this definition, the following theorem says an ideal I of a lattice L is a prime if and only if Gi of L is ideal symmetric. And this follows the outline of the proof. So overall, the conclusion is we introduced a graph of a lattice. This is a new notion with respect to an ideal, and we have obtained some interesting results. More than that, we made an attempt to connect the graph theory with the lattice theory, which really helps us to characterize complete graph with respect to Gi of L. And in future, we are trying to extend these results to different types of graphs. Here we have taken some specific type, we have taken some limitation, but we will try to establish all this characterization for varieties of graphs. So this is what I want to present in this particular presentation, and thank you for the opportunity. These are the references. Thank you.
Very good topic. It's
Yes, sir.
related with the lattices, then groups, and graphs. Okay.
Yes.
Must be thorough with all the three subjects.
Yes, sir.
Really deserves good congratulations.
Yeah, thank you, sir.
And here, anyone wants to ask any question here? Okay, then.
Yeah, thank you, sir.
We will wind up here. Thank you. Good presentation, Harsha.
Yes, sir. Thank you so much. Actually, there is one more field in computer science, sir, that is recently emerging called formal concept analysis.
Okay.
And that also we have connected recently. And
That is
one of the
from
present,
lattices.
yeah, basically it's purely a computer science domain, but from that we can obtain concept lattice, and
Okay.
that we connected to graph theory, sir.
Now, could you connect this with, like, say, we have ideals emerging from rings, right?
Yes, yes, sir.
Basically, rings. In
Yeah,
case
yeah.
of integral domains or field, in field there are only two ideals.
Yes, sir.
Yeah. Could you have any examples?
As if now, I have not anything in that direction, sir. But you gave me a good idea. Maybe I can think of, sir, in that direction.
You can think of, say, like in finite fields.
Yes, sir.
There is a lot of work in finite field and graph theory.
Yes, sir.
Maybe, yeah, there you can relate your topic, lattices.
Yes, sir. Even filters also we can work on, because filters also is a dual of ideal. I'm also planning to work in that direction also, sir, but I have not started in that direction. Maybe after a while we will.
Yeah, certainly you have a lot of scope there. Good.
Yes, yes, sir. Yeah. Thank you, sir. Thank you so much.
Yes. Thank you, sir, for chairing the session. Also, I would like to thank all the paper presenters, those who have presented their paper. Thank you all. And also here we have some other participants, other teachers and all. So I would like to thank those members. And yes, thank you all. Now you can leave the meeting. Tomorrow we shall meet at Microsoft Meets. Thank you.
Four vertices in W resolves the 4 CPP graph. So 4 vertices is enough to resolve the 4 CPP. So based on this, we have a theorem. Let G be a molecular graph of a cycloparafin NCPP. Then the metric dimension of G is n for n greater than 2. And its metric dimension is 3 when n is equal to 2. So these are the references. Thank you. Thank you.
Any question? There is no question. Thank you for presenting the metric dimensions for the chemical compound. That will lecture. Thank you. The next participant.
Next presenter, Vidya Raikar, presenting paper on the topic First Diagram Index of K-splitting of Generalized Transformation of Graphs.
Good evening, one and all. I am Lieutenant Vidya Raikar, Assistant Professor, Department of Mathematics, Government First Grade College and PG Center, Dharwad. First of all, I would like to thank the organizers of this international conference on discrete mathematics and combinatorics to be held on July 22 and 23, 2021. Today I am going to present my paper on a first diagram index of case splitting of generalized transformation graph. Presently, I am working under the guidance of Dr. Ashoka Desai and co-guidance of Dr. Shailaja Shirkol at VTU, Belgavi. So in this paper, we have obtained the explicit formulae for the first diagram index and co-index of a case splitting of a generalized transformation graph. And followed by this, we also obtained the analogous expression for the complements of this splitting of GAB. So let me give introduction for this paper. The vertices of a molecular graph corresponds to the atoms in the molecule and the edges corresponds to the covalent bonds. The topological index is a graph invariant in which maps each molecular graph to the real number. Numerous such descriptors have been considered in the theoretical chemistry and have found some applications, especially in QSPR and QSAR. The topological indices are categorized into two types, namely degree-based indices and distance-based indices. So some of the well-known degree-based indices are the first Zagreb index, second Zagreb index, forgotten index, hyper Zagreb index, Randic index, harmonic index, geometric index, redefined third Zagreb index, etc. So for more details, we refer topological degree-based topological indices. We refer the references given at this numbers. So let me skip some slides. So this is all the introduction given for this paper. So in the present work, we focus on obtaining the formula for the first Zagreb index and co-index of a case splitting of generalized transformation graph SPLK of GAB. So let me give. So here throughout this paper we consider the undirected simple and finite graphs. Where G is a graph with vertex set VG and edge set EG. The cardinality of VG we have taken as n and the number of edges is equal to the first Zagreb index M1. So this is defined by summation of degree of U square for every V belongs to VG, and M2G, that is the second Zagreb index. So this is defined by summation of degree of U into degree of V for every HUV in EG. And the first Zagreb index can also be expressed as M1 of G is equal to summation of degree of U plus degree of V for every H U V belongs to EG. And the first Zagreb co-index M1 of G and the second Zagreb index M2 of G bar. So these are defined by M1 of G bar is equal to summation of degree of U plus degree of V where UV does not belong to EG, and M2 of G bar, it is defined by summation of degree of U into degree of V where UV does not belong to EG. So here for a given graph G with vertex set VG and edge set EG, the two elements VG union EG, we say that the associativity is positive if they are adjacent or incident, otherwise negative. So let AB be a two permutation of the set plus and minus. So then with this permutation we obtain the four graphical transformation of the graphs as G plus plus, G plus minus, G minus plus and G minus minus, where so this is the condition for the adjacency and incidence in a generalized transformation graph. So the generalized transformation graph GAB is a graph whose vertex set is V, G union EG, and alpha beta belongs to V, so that alpha beta are adjacent if and only if these two conditions hold. The first condition is alpha beta belongs to the vertex set of this transformation graph. So these are adjacent if A is positive and not adjacent if A is negative. And alpha belongs to V of G and beta belongs to A of G. So these are incident in G if B is positive and not incidents if B is negative. So this is the condition. And the case splitting of a graph G is denoted by splitting of SPLK of GAB and obtained by adding to each vertex U a new K vertices, that is U dash, U double dash, UK, such that I lies between 1 and K. So this is adjacent to each vertex that is adjacent to U in G. So some of the results we have obtained for the all the 4 types of a splitting graph of a generalized graph. The first result we have obtained for first diagram index of a case splitting of G plus plus. So this is a graph we have drawn for a P4 of plus plus. So this is the proposition we have used for this. I directly go for the result of for this graph. The first diagram index M1 of splitting of G plus plus. So this is given by 4 times of K plus 1 whole square into M1 of G plus M. And the first diagram, the second results we have obtained is the first diagram index for the complement of this splitting of G plus plus, which is 4 into bracket K in plus K plus 1 whole square M1 of G plus M plus N plus M into K plus 1 into N plus M into K plus 1 minus 1 whole square minus 12M into K plus 1 into N plus M into K plus 1 minus 1. Next result we have obtained, that is the first diagram co-index of splitting graph is equal to 6m K plus 1 into N plus M into K plus 1 minus 1 minus 4 into K plus 1 whole square M1 into M1 of G plus M. Next result we have obtained for a graph G. If this is a NM graph, then M1 of splitting of G plus plus, that is the complement of this first diagram index, it is given by 6m K plus 1 into N plus M K plus 1 minus 1 minus 4 into K plus 1 plus K plus 1 whole square into M1 of G plus M. Now second result we have obtained for the first diagram index of splitting case splitting of G plus minus. So this is the graph I have drawn for a case splitting of path on 4 vertices P4 of plus minus. So which is given by, so these are the propositions where this gives the degree of V M into K plus 1, degree of E in splitting graph N minus 2 into K plus 1, degree of V dash is equal to M, degree of E dash is equal to N minus 2. Whereas for a graph G with N vertices and M edges, the order and size of in a splitting graph of G plus minus is given by N plus M into K plus 1 and M into N minus 1 2K plus 1. So this is the result we have obtained for the first diagram index for a splitting of G plus minus is equal to M into Mn plus N minus 2 whole square into K plus 1 whole square. Now first diagram index for the this complement of splitting graph we have obtained. So this as M into Mn plus N minus 2 whole square K plus 1 whole square N plus M into K plus 1 N plus M into K plus 1 minus 1 whole square minus 4M into N minus 1 2K plus 1 N plus M into K plus 1 minus 1. Now co-index, the first diagram index, that is the co-index for splitting graph, we have obtained this as 2m into n minus 1 2k plus 1 n plus m into k plus 1 minus 1 minus m into mn plus n minus 2 whole square into k plus 1 whole square. So this is again a third corollary, that is a co-index, that is the first diagram index for the splitting of a G minus plus. So this is a graph I have drawn. So this is for the case splitting of P4 of minus plus. So this is the proposition which gives the degrees of V, E, V dash and E dash in a case splitting of G minus plus, where the order and size of this graph is given by n plus m into k plus 1 and 1 by 2 n into n minus 1 plus 2m into 2k plus 1. So this is the first result, where the first Zagreb index for a splitting graph of a G minus plus, which is given by n into n minus 2 whole square plus 4m into k plus 1 whole square. So as a corollary of this, so first Zagreb index of a, that is complement of splitting graph, this is given by n into n minus 2 whole square plus 4m into k plus 1 whole square plus n plus m into k plus 1 minus 1 whole square minus 2 into bracket n into n minus 1 plus 2m into 2k plus 1 into bracket n plus m into k plus 1 minus 1. So this is one more result. So let us see the last result for the graph, first Zagreb index, so which is obtained for the case splitting of a G minus minus. So this is the graph we have drawn for the case splitting of a P4 minus minus. This is a path on a 4 vertices. So this graph is a case splitting for path on 4 vertices. So where this proposition gives the degree of V, E, V dash and E dash in a case splitting of a G minus minus, and the order and size of this splitting of G minus minus is given by n plus m into k plus 1 and 1 by 2 n into n minus 1 plus 2m into n minus 3 into 2k plus 1. So let us see the result for this. First Zagreb index for the splitting of G minus minus is given by n into n minus 1 whole square plus m square into n minus 4 plus m plus 3m into n minus 1 into n minus 5 plus 4 into m1 of G plus k plus 1 whole square. So this is the result obtained for the complement of splitting graph, and this is the m1 bar of result obtained for the splitting of G minus minus, and this is the co-index of the splitting of G minus minus. So these are the references we have used for this paper. With this, I conclude my presentation. Thank you one and all.
Vidya.
Sir, good evening, sir.
Good evening. Can you hear me?
Yes, sir. Yes, sir.
Do you have any example of first
Ji, sir.
Zagreb index of graph and graph complement are same?
Graph and?
Its complement. First Zagreb index of
Yes,
graph
sir.
and its complement are same.
Sir, I couldn't check, sir.
Okay. And another thing, have you come across first Zagreb index and co-index are same?
Sir, actually, this is the first paper, sir, which I am
It's a good
presenting.
presentation. Good.
Yes,
Yeah, it's a
sir.
good presentation. There is no
Yes,
doubt.
sir.
Have you
Thank
come across that? Huh? Okay, you can think that.
Okay, sir. Thank you,
Any
sir.
other questions from the participants? If there is no questions from the other participants, Vidya has presented nicely, and
Thank you,
wish you
sir.
best of luck.
Thank you,
Best
sir.
of luck.
Thank you.
Gautam, is there any next presenter?
No, sir.
Okay.
Here we come to end of the session. I would like to thank Professor Pradeep G. Bhatt for chairing the session, and I would like to congratulate and thank all the paper presenters. Thank you.
Thank you. Thank you very much.
Thank you, sir. Thank you, everyone.